C hat. Now, let's interpret this in a slightly different way. To give ourselves a small category in which finite inverse limits exist, it's the same thing as to give ourselves an algebraic structure definable by finite inverse limits, which we will call T lower C. Now, this home underlined left exact functors from C to E, that's just the category of realizations of the structure in E. That's T lower C of E. Now, I'm interested in such structures not for arbitrary categories in which finite inverse limits exist, but more specifically for topoi. It turns out that this can be written as being equivalent to home top of E C hat. That to give an object a structure of this type in E is the same thing as to give a homomorphism of topoi of E into C hat. In other words, there I have my classifying topos, it's C hat. C hat is a classifying topos for the theory TC, but restricted to topoi. On the other hand, in terms of the theory that we have, we know how C can be described. We take the set-centric realizations of this structure, let's say for instance group structure. Let's see what is the classifying topos for groups. Alright. We take the set-centric realizations of groups, we take the category of all usual groups. In there we take those that are finite presentation. I take the opposite category, that will be C. And then I take C hat. So for groups it would be that I take all Ontrian functors from C naught to sets, except I had to put a note here, which was just the category of all covariant functors from groups of finite presentation to sets, and I take and that's C hat. So that's the classifying topos for groups. The category of all functors going from groups of finite presentations into sets. What is a classifying topos for commutative rings, for instance? All right, the same story. I take all commutative rings of finite presentation, and I take all covariant functors from these into sets, makes us a topos. Rings of finite presentation means algebra of finite presentation over Z. Yeah? And that's it. That's the classifying topos for rings. But if I want to interpret it as being contrariant functors rather than covariant functors, as a C hat, namely, I should take the category opposite of two rings of finite presentation. Now that's the category which we can interpret as being the category of affine schemes of finite presentation, of finite type also, that is the same thing of course, over Z. So our classifying topos for cumulative rings is just shove finite type, let's say, in the absolute sense, hat. The category of all pre-sheaves over this category, and I think we have started to work with this category so far and pre-sheave on this category. That's among these pre-sheaves, very interesting ones we have, for instance, schemes, arbitrary schemes, interpreted as being functors from covariant functors from rings to sets. Alright, so I made a little digression in order to show how algebraic structures that can be defined in terms of finite inverse limits admit a classifying topos in a very, very explicit, very simple-minded way. And now I will use this in order to solve problem number 1. And so I want to interpret for a variable topos E, I want to interpret an arbitrary functor from a given small category C into E. I want to interpret it as homomorphism of functors, of homomorphism of topoi. So I should homomorphism of topoi, that's something that among others is left exact. So therefore I will first consider the category C tilde, which is reduced from C by taking the envelope corresponding to finite inverse limits. I add finite inverse limits to C. Now we know that by what we have said before, that this problem has a solution. In fact, C is contained in C tilde as a full subcategory. We like to make this precision. In fact, the construction was that we took Hom underline of C and sets. We took all coherent functors from C to sets, and the opposite category of this. And we took the subcategory C is contained in this as a full subcategory, and we took whatever is generated by finite inverse limits from C. In fact, we can do it in 2 steps. We can take arbitrary finite direct limits, and then we need not add any more except direct factors. We need not make a transient construction. So it's something pretty concrete. These are in fact the objects of finite presentation in Hom underline C and sets. It's another way of describing them. They are also just the functors from C to sets that are finite presentation. So it's something which I consider quite concrete. Now, because of the universal property of C tilde, if E is any topos, modulo if E is any category in which finite inverse limits exist, to give a functor from C into E is the same thing as to give a functor from C tilde into E, which is left exact. Means we have an equivalence between categories Hom underline CE and Hom underline, let's write Hom underline CE is equivalent to Hom underline sex of left exact functors from C tilde into E. And now if we assume that E is even a topos, then this last category, what we have seen, is also equivalent to the category of homomorphisms of topoi of E into C tilde hat, except that you have to take the opposite category. Or if you want to write it otherwise, C tilde is contained in C tilde hat, and the functors which we have here, they form a category equivalent to the functors here that commute with arbitrary direct limits and with finite inverse limits. So we get the construction of the enveloping topos of a small category in 2 steps. First we add finite inverse limits, then we take the head of that. When it was pretty clear once we knew that an algebraic structure defined by finite inverse limits can be represented. When we look at it on top where it can be represented, then of course Hom underline C with values in a topos can be represented too, because taking homomorphisms of a category C into an arbitrary category is an algebraic theory of topos. It's an algebraic theory of the most trivial type, because it makes even a sense for arbitrary categories, not only categories which admit finite inverse limits. So problem 1, I think, now is quite well understood. And what about problem 2? It's kind of nice too. In problem 2, we had the following situation. We gave ourselves an object in delta, but we may assume already that this object, you see, is not too big, that it comes from an algebraic theory. So let's say it's a topos. E is a topos, and we give ourselves a bunch of arrows in this topos. And now for every other topos or multiple pseudo-topos, we are interested in all those delta functors, namely functors commuting with arbitrary direct limits and finite inverse limits, that transform these arrows into isomorphisms. And what we want to do is to find a universal way of doing so, which we will denote by E sigma minus 1, in such a way that Hom underlined within delta of E sigma minus 1 F could be filled with Hom delta comma sigma of EF, where the index sigma means that we take only delta functors that transform elements of sigma into isomorphisms. So we look at this universal construction. And here what we do is much the same as before. We will we can always augment this set of arrows. In fact, we need not even assume that in order for this solution to exist, we need not even assume that sigma is small, as will come out. And not assuming sigma to be small in our statement, we can be pretty free in saturating it with respect to operations. And we will saturate it with respect to finite inverse limits and arbitrary direct limits, something like this. And we will call sigma this new sigma. Of course, I mean, when we have saturated it, I mean, the universal problem will not have changed. This here will not have changed because the functors which we consider transform with these types of limits. And if they transform the limits of sigma into isomorphisms, then also the limits of the enlarged set of arrows. Now this set of arrows, again, as in the case we have dealt with of arbitrary inverse limits, it will allow for calculus of fractions, and it will allow us, therefore, to make a dual now quotient category, and something that is being explained in an exercise in SGA about topoi, that we get by taking arrows that satisfy certain stability conditions, you see, namely those which are true for every passage to quotient, plus the fact that belonging to sigma should be a property of local type, which is consequence of being of local nature. The property of being in sigma should be of local nature. That we have a one-to-one correspondence between these here, between such sets of arrows, and so-called subtopoi of the topos E. Namely, a topoi, I will call what the subtopos is. It's the topos E prime, endowed with a, well, yeah. Maybe I should again make a little digression on subtopoi, because it will turn out that the solution of the universal problem will be a subtopos of E. And subtopoi, geometrically, they are pretty nice. They correspond to the intuition of topological subspace, of topological space. Now, if we have a morphism from a topos E prime into another E, we will say that this is an immersion, an embedding, I'm sorry, of topoi. If, by definition, I lower star, the direct image functor, is fully faithful. Which amounts to the same to say that the I upper star functor, that the left adjoint, is this passage to quotient, is a localization functor. That E prime can be viewed by using I upper star as being a category of fractions of E by exactly those arrows, in fact, that are made into isomorphisms by I upper star. So that's the definition. And of course, if E is fixed, the topos E prime where E is known up to equivalence together with its structure morphism into E when we know its essential image in E by the direct image functor. And therefore subtopoi, you can identify them if you want, to just full subcategories of E that satisfy the condition that they are, well, that they are topoi. So, and that the subcategory is a topos is equivalent with saying that that it's stable under arbitrary inverse limits, because this, of course, let's see, am I saying nonsense? The subcategory should be a topos, no, and the inclusion should be a morphism of topoi. No, that's not it either. No, let's see. What are the subcategories which I get this way? Why I have to tell this? Yeah, there are those which have the property that the inclusion functor admits an left adjoint that is left exact. That's I get results. No, one can't get that along away with anything less. So the topoi over E, such that the structural morphism is an embedding, they just correspond to subtopoi of E, that means subcategories of E, that are such that the inclusion admits a left adjoint that is left exact. All right. Now, this is a story which kind of reminds us of other things which we have seen. We have seen if C is a category, and if we look at C hat, it amounts to the same to give a subcategory of C hat, which has precisely these properties, namely that the inclusion admits a left adjoint, which is left exact, or to give a topology on C. There's a one-to-one correspondence between all possible topologies on C. And these subcategories are associated with every topology on C, the category of sheaves for this topology. To give a topology is the same thing as to give the category of sheaves, which should satisfy these properties. Alright, so this is the story of a subtopoi. It turns out that if a topos is associated to topological space, then let's say the following, that if we have a morphism x goes to y and continuous map between topological spaces, we know that this defines a morphism on top x to top y. And this is an embedding if and only if the topology of x is the inverse image of the topology of y. So which means if our spaces are sober, this just means that x goes into y is injective and that the topology of x is induced by the one of y. And in this way, one sees the subtopoi of a given of the topos top y correspond, let's say, to, well, I should be careful not to say something false. But what is true is that sober subspaces of y can be identified to particular types of subtopoi of top y. However, there are more subtopoi than just those occur in this way. I mean, there are a number of exercises on this again. So intuitively, the notion of subtopos is a generalization of the notion of a topological subspace. And it works just like the notion of topological subspace. For instance, we get the following. If we have a morphism of a topos f into E, then this can be factored to a morphism of f into topos E prime, if and only if the direct image functor, which goes from f to E, factors through this subcategory. Or if you want to say it in the opposite direction, if and only if the inverse image functor, which goes from E to f, factors through this quotient category E prime of E. Quotient category, I mean in the sense of categories of quotients. All right. And on the other hand, there's another exercise in SGA, which says that there's a one-to-one correspondence between subtopoi of E, but I take the strictly full subcategory. You see, so that's up to that I don't distinguish two subtopoi which are equivalent subcategories. Alright, so between subtopoi of E and families of arrows in E satisfying the saturation properties which I have not stated, but which are stated in the exercises, where of course to a subtopos to associate the arrows in E that are transformed into isomorphisms by the adjoint factor here. And conversely, if you have a set of arrows, then you take all objects such that then you take the objects X will be in E prime if and only if how does it go? If and only if for every arrow U in sigma, U going from Y to Z, let's say, the corresponding map from ZX goes to YX is bijective. That's the general correspondence when you have a full subcategory which admits an adjoint. Such that including admits a left adjoint, the correspondence between these full subcategories and the set of arrows that you get in E. Alright. And now let's come back to our situation here. Well, it turns out that E sigma minus 1 is in fact a topos, that this functor here has the exactness properties for defining a morphism of topoi. It is commutes with finite inverse limits and arbitrary Dirac limits, and that a functor from E to F, that the functors from E to F that correspond to morphism of topoi that have our exactness properties that factored through here are exactly those that of course makes the arrows of sigma invertible. And they correspond just to the morphism of topoi from this to this, then to the functor from here to there that have the required exactness properties. So in this way, the problem number 2 is solved in the simplest imaginable fashion. Then it's solved by subtopos. And in fact, we see at the same time, let's say, that every subtopos can be obtained in this way. By localizing E with respect, in the two cases of topoi with respect to a family of arrows, by making arrows invertible. So, if E by chance is already of the type C tilde, contained in some C hat, defined in terms of a topology on C, that means if it's already a subtopos of some C hat, which means then that it will be defined by some topology on C, then the subtopoi of E, they just are in one-to-one correspondence with the topologies on C, which give a smaller category of sheaves. That means with the topology which are finer, where there are more covering families. Therefore, you see, what will turn out is that subseries of a given algebraic theory represented by a topos E, when this topos E is written explicitly as some C tilde with some, you better take a small side, it's nicer. C, you see, subseries just correspond in one-to-one correspondence with topologies on C that are finer than the given topology. So this is kind of pretty. You see here really we make an essential use of this sum of zeros that I had appreciated fully so far. So it just expresses subseries in terms of arbitrary topologies or topologies finite and negative topology. All right, this much about problem 1 and problem 2. And now we can give our theorem of representability. Namely, what are the algebraic series corresponding to delta, to the category of pseudotopoi. Algebraic series are all those that are representable. Those represented by topoi. Moreover, if either topos if the map of I into E, where I is a discrete category, then this functor B is basic, namely I may be good at being generating that as being the indexing set for base objects for our theory, if and only if I is generating, and here it covers all possible senses of the word generating are the same. All right, now let's give more or less a proof of it. All right, we kind of know already that algebraic series are representable. I mean, there's once problems 1 and 2 are solved, I mean, it's a theorem. Whenever problems 1 and 2 have an alternative solution. Because when we make our inductive process, you see, for constructing our theory, at each step we can see that starting with representable series, we still have a representable theory. And in fact, we could follow also the generator, so to say. In fact, if we start, but we will see in this case, is that if we start with the generating set I, you see, which would be this set of base objects, it will go on being generated. So that algebraic series are represented by topoi, I think this is pretty clear. So what we have to prove is the converse. And more specifically this here, that whenever if I goes into E, which is generating, then E represents an algebraic theory on the base objects I. So let's do this. And it will turn out here that we don't need a transfinite construction. It will be done in both 3 steps. Now let's do this. All right. So I guess what we first will do, I mean, we take the base set I. If we want to follow the, never mind, I think it's not worthwhile following the representative, the classifying topoi. And I add the arrows that come from E. So I make first, I transform this, I kind of make this functor fully faithful first. And I put some extra data, namely the arrows, between objects of I that are already in E. And as axioms now I put that the compositions of arrows that we have in E should be true. Should hold true. In other words, if you want, I denote now by I1, if you want, the full subcategory in E generated by I, and I look at the algebraic theory that is defined by I1, you see, with no limits required. It's a theory which works in the category of all categories, which associates to every E home underlined of I1e. It's an algebraic theory even on the category of all categories, so it's certainly an algebraic theory. There are very few axioms, very few data. This we have seen several times, I think. That's an algebraic theory, based of course on I. We have added just a few we have added a few arrows on I, and we have written that some compositor are equal to some other arrows. All right, but I guess let's see. Am I through now? No, I guess I'm almost through. So let's call this theory T1 if you want. T0 was the empty structures on I. So T1 is again an algebraic structure on topoi, because it's an algebraic structure on all categories. And what should we do next? Yeah. What I want to say is that the morphism of topoi of E into F this category is a full separate category of the category of functors from E1 to F, namely those functors which correspond to morphisms of sides of the opposite direction. Those functors that are continuous and that satisfy a certain extra property. So what I want to say is that's it. Yes, there we have it. See, I1 is generating an E, or what amounts to the same. E can be viewed as being a subtopos of I1 hat. It's a full subcategory of I1 hat. You see, I mean that's the definition I recalled of being generating. Or what amounts to the same, E can be written as being some I1 tilde, where I1 is endowed with a suitable topology. In fact, it will be the induced topology by E. Now, as I have said, an arbitrary subtopos of a given topos can be obtained in terms of identifying the arrows. It can be viewed also using the adjoint functor here by making invertible certain arrows in I1 hat. In other words, let's see. There's just one trouble. Namely that I have not yet proved that I1 hat, you see, represents an algebraic structure with base set I. If I had done this, because, yes, I see. The property of a functor from I1 into F maybe we should take this up tomorrow, because I'm slightly mixed up here. I didn't prepare anything like a talk. So I will try to explain the story tomorrow. Somehow more clearly. I think we will wind up getting the algebra 3 and 4 steps.
We'll get a chance to recap a little bit tomorrow.
Yes, that won't take long this year. So what we could do, I mean, there are two kind of things we could do tomorrow. On the one hand, I mean, give lots of examples of classifying topoi, which I think would be helpful. And the second, we try to recapitulate a little bit what we have seen so far. I think nothing is really very solidly done. You see, everything is kind of thin air. Yeah. So.
It's getting better for the money, isn't it? Sure.
Yeah.
All right. So we
That'll be
meet
like-
at
that'll be like-
1:30?
Yes.
Fine, now what, I think you're up at 11?
Yeah, that would be nice.
Yes, and I'll
Tell me,
tell
we can
you.
find out now?
Yeah, I'll
Okay,
find out now.
Okay, I'll be,
Yeah. They had the more professional things would be to see a machinery that corrects mistakes.
Well, this will count.
There's a little need for this. I have to start with rectifying mistakes of the first time. So I discovered, for instance, a wrong statement in SGA, which I gave you yesterday, and it occurred to me this morning.
Well, the statement in SGA is wrong?
Yes.
Oh, you reported it incorrectly, or it's wrong there?
It's actually wrong. You see. I didn't realize how.
Lawvere will be delighted.
So let me recall the situation. There was about strict generators. There was a subcategory C and E. C is full subcategory, and I stated two equivalent conditions, which in fact, I guess they are really equivalent. Anyhow, I don't say anything wrong with them, although I didn't check again the proof. Namely, the functor which goes from E to C hat by mapping E into E hat first to C by the canonical way and then take this restriction functor. This is fully faithful. And then to say that for every x in E, x is the direct limit of all y's of C line over x. So you look at the category C over x, and you look at the various y's in it. So these here, I think I fill in. But I stated that this was equivalent to another condition, namely, call it C here, that for every x in C in E, there exists a family of morphisms yi goes to x, which is strictly epimorphic. Epimorphic, the yi's being in C. Now, what is true, of course, is this one, that if x is the direct limit of objects from C, whether it be this direct limit or any other, then
there is one, yeah.
there is such, that's it, yeah. Now, on the other hand, but the converse is not true, you see, because, for instance, if you take, as I pointed out, I mean, I gave the counter example yesterday, if you take, in the kind of abelian groups, say, take the subcategory, that's it, and that is formed by the two objects, the full subcategory Z and Z times Z, alright? So this will be E. And whereas C will be this here, just Z. And then of course Z times Z is the sum of two copies of Z's. Therefore, I mean, on the other hand, Z is Z itself. So certainly this condition is satisfied. But on the other hand, it is not true that Z times Z is a direct limit of this particular direct system, because this would mean precisely, if it was, of course for Z there's no trouble, this would mean that the functor that goes from E, namely the full subcategory here, to the category C hat, namely to the category, what is the category C hat, where C is this object together with the endmorphisms of Z, namely multiplications by integers. Let's look at the monoid G, which is integers with multiplication. You see, these are just sets on which G operates. And the functor which we have, which goes from abelian groups to sets on which G operates, is just the functor which associates the abelian group, the underlying set on which Z operates by multiplying an object X by N. And it is not true that the functor is to be placed restricted to this subcategory of all abelian groups. So I have looked up what was wrong, and I think you see here it's a good example. when we take the two morphisms from Z into the two summons of Z times Z, then it's strictly epimorphic.
Right.
If we take all morphisms of Z into Z times Z, it's no longer strictly epimorphic.
Oh,
That is, if we add morphisms, something that was strictly epimorphic may no longer be so. Now, this can even, I guess it should be even possible that this happens with just one morphism, you see. If we have a morphism X goes to Y, and if we have a morphism, call it Y prime goes to Y, which dominates this one, so that this one can be factored through here, and if this here is strictly epimorphic. So if it was epimorphic, you see just, then this one would be still more epimorphic, I dare say. But with strictly epimorphic, I doubt it's true. At least the corresponding fact for families wouldn't hold, you see. Now I thought that perhaps the mistake came from the fact, I think there's a mistake which I made several times in the notes. I was so much accustomed to dealing with topoi and such categories, or sites that resembled already the topoi that I described, that I was accustomed always to take sums as being, to take products as being distributive with respect to sums. And therefore, I was kind of not, in several places I corrected mistakes here and there. I took it for granted that if you have a family of morphisms xi goes to x, this will be strictly epimorphic, or strictly universally epimorphic, or whatever, I mean, any of these variants, if and only if the corresponding morphism from the sum of the xi's to x is strictly epimorphic.
well, that's not true. Unless,
I guess it wouldn't. Let's see, strictly epimorphic.
right.
No, of course, I mean,
What means
it is not, because if you take,
You want the map into the
this is a good
pro-
example. If you take all morphisms from Z into Z times Z, you see, they don't form a strictly epimorphic family. When you take the sum of them, they do form a strictly epimorphic morphism. A strict epimorphism. Because a selective homomorphism of Euclidean groups is a strict universal epimorphism. It's a fact.
What means strictly epimorphic? What means strictly epimorphic?
A strict epimorphism is a epimorphism such that Y assumes that the fiber product exists, at least. In this case, the simplest is to say that Y can be constructed from X as a quotient of X by the fiber product. So the terminology is designed in such a way that the quotients that are strict quotients, namely so that the map to the quotient from X to Y is strict epimorphism, correspond to the equivalence relations that are
But all I do need though is that I commute with, let's suppose that I've got fiber products, okay?
that is
Suppose that this commutes with the.
in any case,
I do need universality.
we shouldn't
I know.
We shouldn't replace, let's say the following. If fiber products exist, and if they are distributive with respect to arbitrary sums,
Then,
then in the family is strictly epimorphic.
If and only.
If this one morphism
okay,
is strictly epimorphic.
okay, fine.
But otherwise it is not so. And I made, you see, and sometimes I made the misstatement. I said at a certain proposition that if all epimorphisms are strict, or and in fact I meant I really had to. I really didn't mean that if all epimorphic families are strictly epimorphic. But let me give another statement here. There you have an implication, but because after all I did prove something in this proposition, although I misstated what I proved. If we assume, call it, I will state a property which will imply these and which resembles very much this one. For every x and e, there exists a family of morphisms yi goes to x, which is with the yi's in C, such that this family is strictly epimorphic and universally epimorphic. The two together. Then things work. Maybe I should give the proof after all, you see. Let's
You like proofs?
I guess it's true, yes. At least let's say the following, that if we have, let's say this much more, if we have the situation I just said here, we want to conclude that x goes to y is strictly epimorphic knowing something here. If this here is strictly epimorphic and universally epimorphic, then this one will be strictly epimorphic and universally epimorphic.
Mm-hmm. Yes.
There's some diagram shading.
Yeah, that's true, that's true. I'll admit that.
All right. Now, I think that I didn't really write down the proof. I had just 15 minutes left there before lunch at Philip's place. But I think this would be true. I wonder, should we check it now, or maybe we don't really need it so much for the seminar. So let's put an extra interrogation mark here. Let me say the idea, of course, of the proof, and we will see what comes out. So that's it. Yeah, I think I can prove it. All right. So if here you have the family of some yi's go to x, yi's in C, which is strictly epimorphic and universally epimorphic. Now take the family of all y go to x. You see the family which is parameterized by C over x. So which comes in, which enters in the condition B. Now this will also be strictly epimorphic. That's really what we need to know. It's strictly epimorphic and of course universally epimorphic. All right. So now what we really need here, what is equivalent to B, is that this family here of morphisms from y to x parameterized by C over x is strictly epimorphic. So this would be equivalent. We find the family of all y to x, y in C over x is strictly epimorphic.
Right, no universal.
Also, now C prime implies B prime. Now let's prove that B prime is equivalent to B. B of course implies B prime, we have already noticed, right, when we prove that B implies C. So let's prove now that it implies that this B prime implies in fact that x is not only, that x is in fact the direct limit of these y's. So I have to prove the following thing. I look at any z, so the function represented by z, hom z x, let's say hom z variable t, let's say t goes to hom z t, I will denote it by f. F of x into the product of all f of y's, where y varies over the category C over x, is injective. That's in fact the assumptions. B prime.
Assumption, yeah.
Not only for x, but for every x. For this one x, but for every x. That was the assumption. Here there's this quantificator, which I didn't write down for every x. Then we take all these here, then this is strictly epimorphic. Alright, now what does it mean that this family is, alright, is in fact strictly epimorphic? That says something more. Here we have only expressed that it's epimorphic. It says that the subset of the product, which is the image here, can be characterized by the following property, that for every family of morphisms from any given object T into the y's, so let's say alpha lower y, where y is an object in C over X in our indexing set for our family of morphisms. But for every such family which has the property, how should I say this? Is this the whole family I have to take? No, it's not the whole family. I have to say the following. That whenever we have two objects in here, y prime and y second, that means just two objects of C lying over X. That's all. Of C. And whenever we have an object T mapped into y prime and y second, in such a way that the square is commutative, T being an E only, then we demand that the element that we have taken, on the other hand we have a system of elements here, we want to express the condition of this. Psi y, let's say, in f of y. See? We want to express a condition that the psi y's belong to the image of fx, and we want to express that for this is necessary and sufficient, that for every such diagram, the image of psi y in f of t is equal to the image of psi y prime in f of t. Because f of y prime and f of y second, f of y, I'm sorry, that was y prime and y second, I wrote down. Fy prime and fy second are both mapped to ft. And that's a very familiar condition, isn't it? I mean, the condition for expressing that f is a sheaf, for instance, for topology. So, using condition v prime, that for every x, the family of all morphisms from C, objects of C to X, is strictly epimorphic, we want to prove that for every X, if you look at the map of Fx into this product, the image consists exactly of those systems which satisfy this condition. Alright? That's the assumption, I'm sorry. That's the assumption here. That's what expresses that y goes to X is strictly epimorphic.
Sure. Yeah.
And what we want to prove, that's it, that f to x is in fact the Dirac limit of the y's according to this system. That means, what does it mean that's the Dirac limit? It means that f of x, for every f defined by a z, consists of all those systems of elements psi y, where the condition here holds, but with psi and c only. That's it. And now, what I have to prove is that if the condition holds for t in C only, then it holds also for any t.
Okay.
And now, take any t, not necessarily in C, and now use again the property here by replacing x by t. Then we know that we can find a family of morphisms from yi's, let's say, in C to T, which is, well, strictly epimorphic, but epimorphic would be sufficient here.
Mm-hmm.
All right? And now, that's it. And now what we know is that our set of elements, psi y, etc., that psi y prime and psi y second, become the same, perhaps not a priori when we go over to f of t, but when we go over to f of yi. and we want to prove that then they have become already equal in
Okay.
f of t, but this comes from the fact that this system being epimorphic entities have injected into the product of their yi's. Therefore, in fact, my argument in SGA was right, except that I admitted implicitly that if you have a strictly epimorphic family, any larger family is again strictly epimorphic, and that's not true. Now, when I spoke of, in the seminar these last days, of a strictly generating family, I definitely had in mind these two
Conditions there.
properties,
Okay.
the stronger ones.
But obviously the other one is the more convenient one, so, let's see.
Which one is more convenient?
Well,
This here, I mean, it's
for the
weaker
functorial arguments, obviously, this one here is the proper one, because that's the one you can link with the others. But in terms of finding such a diagonal, finding such things in more ordinary terms, that's this.
So if you want something which sounds like this one, you see,
Yeah.
then then we should take this one, that we can find a family of epimorphisms, a family of morphisms into X with sources in C, which would be strictly epimorphic and universally epimorphic. But, yeah, it's kind of funny, you see, when there's so much accustomed to some categories where everything happens in a certain way, that sometimes you see just drop the assumptions that you just forget that it's not always so. Maybe I've never noticed it, that a strictly epimorphic, probably I haven't, that a strictly epimorphic family doesn't remain
Not
so
necessarily.
when we add more things to it. After all, there has something to be proved, of course. You see, when you take strictly epimorphic and universal, you see, I mean, the same with descent conditions, you see. And you have to do some diagram chasing.
But is that true? I thought about that.
After all, when you write it, I mean, if you just write the definition, namely that y is a quotient of x by this double arrow, and you want to prove that this is true, and you assume that you have another arrow here
precisely.
for which it is true,
Yeah.
and you assume moreover that there is such a morphism. So why should it be true here? I mean, one sees that there is something to be proved, and we try to prove it. Then you see what
You
is
need
lacking is the following.
universal for that.
Then you wind up with writing down, rather let's put here y prime. You wind up with a diagram like this. You have here x goes to y, here you have y prime goes to y. You see? The fact that there exists a y morphism, you interpret by saying that there exists a section of x prime goes to y prime after we make the fiber product. And then you make some diagram chasing when you complete the diagrams here with adding everywhere fiber products. So then you have a pretty standard looking diagram here.
Right.
And then you chase some diagrams. And what you see, what you need as something more than the fact that this here is an strict epimorphism. In other words, that this diagram transformed by f is exact. In order to prove that this diagram is exact, you need to know that fx goes to fx prime is injected. That means that this morphism, which we assumed strictly epimorphic, after we make the base change in it by this x goes to y, so that we get now x prime goes to x, that this should at least be an epimorphism, perhaps not strict.
Yeah.
All right. So,
Yeah, that's right. That it suffices for that to be, but that amounts to saying in this case here that x prime over y is going to be what you want is the hypothesis that it's universal.
yeah.
Yeah.
Yeah. So, I mean, the weakest condition we can put here is strictly epimorphic and universally
Epimorphic, but not universally strict epimorphic.
So that's not necessary.
That'll suffice. Just
Although this is really is a beautiful notion, you see, which gives the canonical topology.
which for
Universally strictly epimorphic. It's strictly epimorphic and it remains so after any base
it
change.
remains strictly epimorphic after
After
any
any
base
base
change.
change. That's more than is needed.
For the canonical topology or here?
No, for
Here all you need that it's remains an epimorphism after base change as a family.
Yeah. In the same way, for instance, you assume that you want to prove that x goes to y is a morphism of effective descent and morphism of 2 descent. So what you have been doing so far was something like 1 descent. And assume that you can find y prime goes to y, which is of effective descent, and such that this arrow can be dominated by an arrow like this. Then the diagram chasing, when now you have to add, of course, a little more here, will give you the following. This being, so you look at the full diagram with all these arrows here. Now that's it. This, if you assume that this morphism of 2 descent, that this morphism of 1 descent, and that this morphism of 0 descent, then the conclusion will be correct. That namely that x goes to y will be of 2 descent. Of course, we assume already that there is a section here, so that for these things here, all of them, we know that they are of 2 descent. And then there's some diagram shading on x. So, really the universality is really a very important condition. And there's some things here you see which I thought were true, although I didn't know. That I need to be careful, but I didn't know it enough. That just break down and you don't put in some condition of universality.
No, but clearly in either case, whether we can do this or not, then the two conditions A and B are clearly equivalent. There's no problem with that.
Yeah.
Yeah, that's no problem.
And all right, and they are going to be prime, that's the argument I just made.
Yeah.
There's no problem. But this is a rather particular system of arrows, taking just all arrows, you see.
What is B prime in vector? What's the statement for B prime?
For every x, if you take the system of all arrows from objects of C to x, this is strictly epimorphic.
Okay. That's that statement.
Yeah, that's equal to B. I mean, what I really do prove is sequence between B and B prime, but I misstated it as meaning B prime as being C, because I assumed that if you have a strictly epimorphic family, any larger family is strictly epimorphic. Alright, so I don't think, however, that anything essential which we have said so far is crashing down.
No, not about
So let's say when I define strictly generating family functions, speaking about these accessible categories, indeed it was condition B and C, or B prime I had in mind. Now, so yesterday we solved problems 1 and problem 2 for topoi, and then we gave some extra material on topoi. And then we stated a theorem, which I also misstated. So I will give the correct version now. I have time this night to look it up a little more carefully. So the correct theorem would be the following: that R be an object of delta, pseudo-topoi. Then first the rather vague statement, I mean not very precise statement. R is algebraic, and the theory it represents is algebraic if and only if R is a topos. And B, if we give ourselves a function from a discrete category into R, we wonder when is this functor basic, namely when can we consider I as being the indexing set for base objects of an algebraic theory represented by R. So B is basic, if and only if I said the subcategory of R generated by B of I, the full subcategory, is strictly generating. That's not exactly it. I mean, that's too strong a condition. You should say if and only if the subcategory, category full subcategory of R consisting of finite products of objects within which.
Yeah.
Consisting of finite products of objects in VI is generating or strictly generating that down to the same theory of what's to look for either. Right. Now, I think you better do this theorem very carefully because, of course, in the general nonsense about general exactness conditions, we more or less prove that if problem 1 and problem 2 are satisfied, then any algebraic series representative, etc. But we did it, you see, we were not too careful in our statements of problem 1 and problem 2. We never were too sure whether the categories which we were looking at were small or not. So, in fact, the proofs I gave, I think, are perfectly right when the diagrams that are considered for the exactness conditions and for the existence of limits, when these diagrams, when this bunch of diagrams is small, but this is not the case in the case of topoi. And therefore, I think it's better to take this from scratch and just to prove that it's true. Now we have, we are really on firm grounds and we can really prove things. But before doing so, yes, let's make a few preliminary remarks to put us into shape, so to say. Let's first, for instance, prove that if R is a topos, so the weaker statements, if R is a topos, then R is algebraic, because this is. So this seemed to be kind of strange. So assume R is a topos. Take a generating subcategory C in R that is stable under finite inverse limits. C generating small, first of all, generating and stable under finite inverse limits.
So let's take the generators that you're given and just expand them a bit, perhaps. Yeah.
Yes. Yeah. Yeah, you add finite inverse limits to them. And then we still take direct factors if needed, if it's not stable yet. And there we are. By the way, even if we have to iterate this operation countable number of times, the category will still be small. I mean, there we have no trouble at all. All right. And now look at this. Look at this theory. Let's call this theory tau lower C, which associates to every pseudotopos E all left exact functor, let's say one of this, yes. Of C into E. So that's in fact an algebraic theory defined by finite inverse limits. That's, it's exactly in this way that we get such algebraic theories. And now, and we know, of course, that for theory, this is an algebraic theory for topoi, which is just restriction to topoi of this theory. If we restrict E to be topoi or pseudotopoi. And in fact, we have seen what is the representative topos for this. It's something very familiar. It's just C hat. In order that the functor, you see, we have seen that the morphisms within delta of C hat into E, so they would correspond geometrically to arrows in the opposite direction between the topoi, but here, as well, for the time being, in the context of delta, so arrows that are commute arbitrary direct limits and finite inverse limits, they correspond in one-to-one way to functors that are left exact from C to E. Recall that any functor from C to E corresponds to functors from C hat to E that commute with arbitrary direct limits, and the left exact functors here correspond to the functors here that are more over left exact, namely that correspond to morphisms of topoi or pre-topoi, even only pre-topoi. So therefore, this algebraic theory, you see, is certainly representable by a topos. This is what we did yesterday. And now, of course, let's look at the morphisms of topoi going like this. So morphism of topoi, because let's work in the yoga of delta, so the arrows are in the wrong direction if you want with respect to the rhythmic intuition. But let's forget the rhythmic intuition for the time being. Well, as C generates R, you see, R is just C tilde. And we have seen that the functors from that's the morphism of topoi from a C tilde to E, they just correspond to continuous functors from C into E that are moreover left exact. So therefore the category represented, the series represented by R, T lower R, appears as a full subseries of the series which we call tau lower C, which is also T lower C hat. And in fact, it's the category of Hom delta that we're interested in, of RE within Hom delta C hat E, which we identify as before to Hom 6 of CE. You see? So this consists of those functors in here that are not only left exact, but which moreover are continuous, and that transform covering families of C into covering families. But that's again now an axiom. Because I mean, series of C, they define constructions, and after all, the constructions are the limits of R. And we write that certain families within C, which is contained in R, should be isomorphic. And in fact, it's a small number of axioms that we are writing down here. Let's make the following general remark, perhaps. Assume that we have, so let's say it in the following way, yes. Assume that we have a topos R, and therefore a series TR, and assume that we have another represented by it, that we have another topos R prime, and therefore theory T prime equals TR prime, and that we have functor from T prime into T, which of course will correspond to a morphism within delta of R into R prime, which is fully faithful. That means that for every E, you get an embedding of the capital T prime E, a full embedding, into TE where E is in delta. Well, I claim then, first of all, that this means that this functor here turns R prime into a subtopos of R. You see, this is a localization factor. And that moreover, this passage to a category of fractions can be obtained by just a small set of arrows in R that are being made invertible. Therefore, if we know that R is an algebraic theory, you see, which in fact we know already, we just proved it. Therefore, R prime is deduced from this algebraic theory by adding as axioms that these arrows become invertible. So, let's prove this. This will be kind of trivial. So what we know is that for every E, when we look at Hom lower delta of R prime E goes into Hom underlined lower delta RE, we know that this is fully faithful. And it's an exercise in SGA, but it should be trivial anyhow. That this would imply that this arrow called F upper star if you want, and let's look at the F lower star arrow. That is, it's adjoined at where I put it right underneath. That is, it's joined at the right side. So we have to prove either that R prime goes to R is fully faithful, or that F upper star is a passage to a category of fractions. And why is it so? Should be something like a
reality, I think. It's easier when
Sure.
this, of course, can be viewed as being the category is opposite to the category of functors that go from E to R prime that are commuted with arbitrary inverse limits and such that their joint which then will exist is left exact. And the same for the arrows for this category, which can be interpreted in terms of functors going from E to R, and then the functor from one to the other is just composition with this functor F lower star. So we have to prove that if the functor which goes from underlined delta, now we shouldn't call it like this way, call it home prime if you want, underlined delta ER prime, here we're taking that joint functor is going to home underlined prime delta ER by just composing a functor phi having the property stated with F star on the left, that this should be a full embedding. Yes, for instance, we can, yes, because we can say it in the following way. This, yes. I think this neither of this helps. What I will do is the following. I will take for E yes. Yeah. Will I be able to prove it now?
What do you want to show? I'm a little confused. What are you showing?
I want to prove that F lower star is
indeed the category.
fully faithful.
All right. Okay.
All right. Well, I don't remember the proof. Okay. So maybe we better.
What do you give it? That R prime is the category of fraction.
I'm sorry, I think that.
Confused. What do you want?
I assume that we have two theories
Right.
represented by R prime and R. I have a functor in between them,
Okay.
which means that we have a functor in the opposite direction between
R and
the categories that represent them.
Right.
I assume that this functor here is fully faithful. And if I every E that this functor is fully faithful, then I assume I have a theory and a full sub-theory. And I want to prove that this corresponds to the situation of a topos in the subtopos.
Okay.
And
that's-
there's something to be proved. And apparently, I get stuck here again. Now let's see. Maybe, yeah. Maybe I want to remember the proof here. Therefore, maybe we better, all right, maybe we at this point, I'm not sure we are going to use it anyhow. There's an exercise in SGA concerning subtotal, which says just this. I don't
Yeah,
know.
that's the statement of this, isn't it? Yeah.
But maybe I won't use it. So I assume already that we have a subtopos. In this case, of course, it is true, because I mean, passing to quotient, you see, gives you. I mean, that's how you capacity to quotient, how we have it by a set of arrows here. That's how we have obtained this situation.
That's certainly
You
true.
all right, in this direction, it's all right. Now, the point I want to make is the following. It wasn't really so much about this equivalence, although I'm pretty sure this equivalence is true, that subtotal correspond to full subtheory that are representable. But the point I want to make is that R prime can always be described in terms of R by a small set of arrows.
Yeah, that's
And I mean, this is pretty clear, because R, we can describe it by
small.
generating subcategory small, subcategory C, S being R equivalent to C tilde, where C is endowed with induced topology. And now, within C tilde, R prime appears as a subtopos. And therefore we know that R prime corresponds to a topology on C, another topology on C, call it T prime. T was a given one. Well, let's rather call it small tau because T were already the series. So on T we have another one, and T tau prime, which is finer, with more covering families and therefore with less sheaves, so that R prime is C, comma T tau prime tilde, whereas R was C, comma tau tilde. And then what are the functors from R prime into a topos E, inverse image functors? I'm sorry, from R into topos E, that factor through R prime, we can interpret everything in terms of functors on C, from C into E. And now we have exactly those functors that are continuous not only for the topology tau, but for the topology tau prime. And this means that certain, like, if C is stable under finite product, for instance, as you may assume, then this just means that covering families of C are transformed into covering families in E, but this again a small family. This is a small number of axioms. So to say that certain arrows are covering, I mean that it's an axiom. It means that a certain sum is met by an epimorphism. It means that another arrow which can be constructed in terms of the data is an isomorphism. In fact, if C wasn't stable by, we can always take it if you want stable under finite inverse limits. If it wasn't, in fact, then we could directly, we have expressed continuity of the functor in terms of saying that certain cones that we construct in C in terms of certain direct systems on C directed to elements of C should be transformed into exact cones. I mean, this again is, each of these is an axiom, making some arrow invertible. So, therefore, whenever we have a topos and a subtopos, then in terms of the series they represent, the second series corresponding to the subtopos can always be deduced directly from the first series by just adding a small number of axioms. So that's something in which is, and some more precision to the fact that both are representable. It's not that clear that if you're in a modular context with any data you see, if you have a full subtree of a given theory, it's not clear that we can obtain it from the given theory by just adding axioms, that we don't have to add also arrows and make some transparent construction. I don't know if it's true, but here at least it works well. Now I want to make also another comment before setting to this here. It's about two direct limits in the category delta, which would correspond to two inverse limits in the category of topoi, for instance, products of topoi, fiber products of topoi, etc. And the statement is, there's made a big fuss in the seminar SGA even about these two inverse limits. There's a huge preliminary, etc. And then one doesn't even prove the existence of two inverse limits of topoi. One does it in a very painstaking way in the filtering case, and it is explicitly stated that the theorem, surprisingly enough, is stated is not trivial. But in fact, everything is completely trivial, as you will see, without any fuss. So let's see the situation. We have a direct system, or pseudo-direct system within delta, so it would correspond geometrically to an inverse system of topoi, but need not be filtering, I don't mind, it's anything. So we have an indexing category downstairs here. But, and we want to construct an object of delta, and arrows, a system of arrows from the EI into EU which would be, which would have the necessary transitivity conditions, so that for every arrow between these topoi coming from an arrow downstairs, that this triangle should be commutative up to a given isomorphism, and then with transitivities about the isomorphisms, but letter 9, I mean. Let's kind of handle them with a grain of salt, as if it was just a usual diet system. All right, and for variable e, so we want to represent the functor, the two functor, which as every e associates the category of all these systems. And we want to find something universal that does it. Perhaps we have put R here instead of E. And the universal thing we want to find is an R, so that whenever we have these things into an E, it factors in essentially unique ways through R. In fact, we want that the category of all these systems for a given E is that the function which goes from the category of all these systems, that goes from the set of delta homomorphisms from R to E by composing to the category of all those systems should be an equivalence of categories. And that's the usual story of true representation. And here of defining what a two-diag limit is. Now what we will do is the following. We will choose in each of the RIs, we will choose a subcategory Ci that is small in generating. And in order to be more at ease, let's say, to make the construction smoother, but we will also see that the Ci's are stable under finite inverse limits. And it's pretty clear that we can match them in such a way that these transition functors going from the Rj to the Ris map Cj into the Ci's. If it wasn't so, then by saturating, you see, it's a very easy exercise to show that by replacing every Ci by a family of subcategories that are, that is the family being small and all subcategories being small, taking the union of these, it will be all right. So what we would do is to take all, for a fixed I, we take all possible arrows from Rj into Ri, and I replace Ci by the union of Ci and all the images of the Cj. And then I add to this, in all possible ways, finite inverse limits. And when I have done this, then these calculus will map the ones into the others because these functors are left exact. And pretty clear. Or else, if you want to be sophisticated, you can use cardinal filtration and say that for pi big enough, these functors, as they are clearly accessible, they can use arbitrary like limits, filtering like limits, you see. They will transform pi accessible objects here and pi accessible objects there. And we take for all pi accessible objects. So I mean, we have a choice of how we do this. And in terms of this, everything will be trivial, you see, but because now, of course, what we want to represent is the category which we will call home, lower delta of the diag limit within delta of the Ri's into E. I mean, this category doesn't exist yet, but this home underline does exist, you see. It's this category of all systems of delta functors from the Ri's into E that match together, of course, with this compatibility data. So this can now be viewed as being mapped into the corresponding system, but of functors of the Ci's into E. Right? Because primary functor from Ri into E, I take its restriction to Ci, and then we have such a compatible system of functors with values in Di, they restrict to the Ci's to give an analogous compatible system. So we get home delta. I'm sorry, home now cut, I should say, of the diag limit, the two diag limit within cut of the Ci's and E. We get such a functor, functorial for variable E. Now, the diag limit within cut exists, the two diag limit. And this is a very silly construction. I take the disjoint union of the Ci's, I add all arrows that are in the Ci's, I take as relations those that we have already in the CIs, and those which come from these functions. I mean, that's a very silly construction to be made. You can do it also by taking the filtering, the fiber category defined by the system, by the system of functors. You see that when it's a category lying over the category I, and I take second order fractions of this, where I make invertible all Cartesian arrows. I mean, there are various constructions, standard constructions. So this here can be just viewed as being home underlined in the category cut of C and E. And now this here, because of solution to problem 1, C is a small category here, this can be viewed as being home within delta of some that's it, of some topos, call it S if you want, into E, where S now is a topos, it's the enveloping topos. Remember that we obtain it by adding finite inverse limits to C and then taking the head. That's the construction. And of course, because the CI we are taking generating in RI, you see, this here is a full embedding. Therefore, the series that we want to represent by a topos, here for variable E here, it consists is a full subseries of one which we know to be representable by a topos, which is algebraic. So now, of course, we want to prove that it can be expressed by a small set of axioms in terms of this series here. We don't know yet that this series, of course, is algebraic. Otherwise, if we could refer to what we didn't prove 10 minutes ago. But in fact, I think it will be pretty easy, because all we have to express now is the following thing. We have our C. Let's make our little drawing. We have our C here. Together, R is not yet constructed, but C is constructed. Together with the functors going from C, from the various CIs into C. And now we have to take, and C now is contained in the category S, you see. And now we have to take all those morphisms of topoi from S into E, or those delta morphisms, namely all those functors from C into E, arbitrary functors from C to T, which have which extra property, that when we restrict them to CI, there should be a restriction of a functor of Ri into E, that is a morphism of topoi, that is a delta functor. But this just means that, remember that Ri being equivalent to Ci tilde, this just means that the functor from Ci to E is left exact and is continuous. So we have to express that certain cones here, when we look at them in C, become exact in E. So that's small bunch of axioms. And then we have to express that certain families here that are covering here, in fact, when we look at the corresponding families here, become covering there, become epimorphic there. Other bunch of axioms. Which is small again. So there we have it. And moreover, all right, so the series is algebraic, but in fact that's not so much what I wanted to see. What I wanted to see is that in fact, now we have our universal, the solution of universal problem, namely, we take R to the S, where I make invertible the arrows, which I have just said. Now this with the grain of salt, that is the one that we take in delta. That just means that we, as we have seen yesterday, that we stabilize sigma with respect to base change and localization with respect to finite inverse limits, let's say, and arbitrary right limits. And then we pass to the category of fractions. And that's the solution. So then we have our topos. So really, these morphisms of topos, you see, they are so convenient to describe, you see, in terms of any small subcategory that generates, by taking the functors of the subcategory into another topos that satisfies some very concrete conditions. Left exact essentially if the category is stable under higher inverse limits, which makes things simpler. And then transforms covering friendly and covering friendly. And then, I mean, to make these direct limits, they are even now I consider them to be even more trivial than the inverse limits in the category delta, you see. Because there, for inverse limits, we have the problems of the generators that occur. But here the generators are built in the proof. Let's see, you see the direct limit of the CIs in the category of cut, in the category cut. It's this category C that is generating. So generators, we have them. Whereas if you take an inverse system of PIs, of RIs, and if you take the two inverse limit within cut, you see, then it will satisfy the same exactness properties as the RIs, so this will be something in delta, but we still have to prove it's a topos, we still have to prove it has generators. And this is slightly delicate. I mean, I gave the statement, when was it? Yesterday, yes. No, this was the day before yesterday.
What was the idea? What was the
about accessible categories, remember. And you have a finite category, like here, the two fibers are the RIs and the transition functors. I'm sorry, the base change functors between the RIs are assumed to be accessible. Here, in fact, they can move arbitrary direct limits, so they are certainly accessible. Then the fiber category is being accessible, then the inverse limit is accessible. The two inverse limits are accessible. That means has generators. That implies, for instance, has generators, which is what we needed still in order to know it's a unit topos, which is then much better than inverse accessible. See? But here, so this may be a slightly delicate to prove this existence of generators. You don't see them right away. But with the other, it was complete reality. And now, let's prove this here. Necessary and sufficient condition. Alrighty. So let's prove, for instance, that it's necessary for this to be algebraic with space I. And therefore, we have to take up the various steps of the construction of an algebraic theory and see how we can follow it. So the first step was to take a base set and to take the empty structure on objects based on objects indexed by I. And here I look at the phi category admitting finite products generated by all elements xi if you want. So I look at all possible products xi to the ni, where all of the exponents ni except the finite number are equal to 0. You see? So this category is in fact equivalent to the category of opposite to the category of systems of finite sets indexed by I, all of the finite sets being empty except the finite number. So finite sets opposite to the power I, but the power between parentheses, because I take all sets in a family of sets being empty except the finite number, because I want only a finite number of exponents here. So that's the category we start with. So we add products. On this category, call it J naught if you want. And then R naught is obtained by just taking J naught hat. You see, it turns out that if you add to a discrete category arbitrary inverse limits, in fact, because we don't have any arrows between the elements, it's just the same as finite inverse limits is the same thing as just adding finite products. That means in the opposite categories, it would just mean taking finite sums. or if you start with a point, for instance, if you want to add finite limits to just a category, the point one point category, if you wind up with a category of finite sets. It is as if you had taken only, as if you had added only like sums. Alright, that's the first step. So here the map from I into R naught, let's make a little diagram in the corner. We have a map which goes from I into R naught, but which vectors through J naught here. So we have added through I finite products, and then we have a functor here from J naught into R naught, which commutes with these finite products. And in fact, a functor, from the category R naught to E, and morphism of if E is delta, and delta functor from R naught to E can be viewed either as a functor from I to E, see just an element of E to the I, or as a functor from J naught to E that moves with products. It's kind of good to follow what is happening on the lateral diagram. Now, a second type of things which we will do is to add axioms. So what we assume now is that we have already an algebraic theory, call it R alpha if you want, if you think of a transfinite construction, and based on some I, you see, we know already that the subcategory generated by products of objects of I is generating. We want to prove something here, and we will do it by transfinite induction. Alright, that means that if you look at the factorization of this through J naught, you see, because I is a functor from the discrete category into R alpha, so it factors in a unique way through a functor from J naught into R alpha. It commutes this product, and we assume that this is generating. Alright. And now what I do in order to add axioms, I take a bunch of arrows, a small bunch of arrows, sigma alpha and R alpha, and I look at the subtheory of the theory we have already, which is obtained by making these arrows invertible. So that's an operation which is familiar to us. It's just this new topos, which here this operation is in the category of topoi. If I want it to be the same as the operation in the category of categories, I should put a tilde on this, namely saturate sigma alpha with respect to the topos operations. Alright, so let's write. So the new theory is represented again by a topos, which is R alpha sigma alpha minus 1, which has the same underlying objects as R alpha. It has just different arrows. The arrows here, the set of arrows here is the quotient of the set of arrows in here. That's all. And now, of course, because J naught generates R alpha, that's what we assume, it also generates all this R alpha plus 1. Because the objects are the same. Therefore, in this step, certainly does check with our theorem. Now, third step, add arrows. So here we assume that we have the situation as before. I goes to R alpha. And that we give ourselves a bunch of arrows between certain objects. We add a bunch of arrows between certain objects of R alpha. So that means, how will we put it? Well, I mean, I have to explain how it is done. We give ourselves a set, a small set, and we give ourselves a map from H into arrows of R alpha. Into objects of R alpha by itself. That means H are the arrows we add, and for every arrow we should give what is its origin and what is its extremity. For the time being, we don't give any relations between them. This comes under heading 2, under adding axioms. And here, yes, The substory of the theory we have already, which we know to be represented by R alpha, by the inductive assumption, is the one in which we want to take the following category for every E. We take, well, I mean, all delta functors from R alpha to E, together with some extra data. For every object in H, an arrow between the image in E of its called source and the image in E of its extremity. And for variable E, this makes a theory with respect to E. We want to prove it's represented by some topos. You see? And we want to prove, moreover, that if R alpha plus 1 is a topos that represents it, we want to prove that J naught generates R alpha plus 1 in order to shape our theorem. And all right, here I think the nicest thing to do in order to make it nice intrinsic description would be the following. H, let's look at the set of objects in R alpha. You see, call it something like T or S, let's see, that's it. Let S be the subset of R alpha, of the objects of R alpha, consisting of all sources and all targets of the arrows that we want to add. And now look at the free category generated by these objects here and the arrows that we have been adding. I mean, this is a pretty standard construction in category of set in the tree of categories. This means that for a variable category now, it need not be a topos. We want to represent the functor which associates, I mean, the following. Functor C goes to, see the variable category, C goes to the set, how should I say? Well, to all diagrams of type S, H. You see, we have a map of H into S times S now. That is a double arrow from H into S, so that's a certain diagram. Here are the arrows there. It's not yet a category, it's a diagram. And here are the vertices, and here is, for every arrow we say what is its origin, what is its extremity. And we take in primary C the diagrams of type this here. For this diagram D, diagrams of type D, and we know how to diagrams of type D is within C, and we know how to transform morphisms diagrams, the category of diagrams, into a category of functors. It's a free category generated by diagram. Or this DT that you want. The category defined by diagram. So, all right. Therefore, what is the functor that we are, the two functors that we want to represent? For every E, we look on the one hand at hom lower delta of R alpha E. On the other hand, we look at the category hom underline of, let's say, of the diagram D into E. But we can express this, if you want, as a hom within categories of D tilde into E. But on the other hand, we don't take them arbitrarily, we take them in such a way that they match. We take those homomorphisms of diagrams from D into E that on the elements of S are just induced by the functor we have here. That is, in fact, we take the two fiber product over hom underline of S and E, where S is viewed as being a discrete category. So that's in fact for variable E, that's the theory we want to represent. And now this hom lower cut, you see, can be viewed also as being hom lower delta of rho the delta tilde, where rho is the enveloping topos of the category D tilde, which we obtain by adding final inverse limits to D tilde and then still adding, then taking the head of this. And the same here for S. This here can be viewed as from OSE. So what in fact we do have is, as following diagram, we have R alpha, we have OS, we have rho of D tilde, we have rho S. They form a certain diagram of in delta of topoi. The functors here, of course, are functors in delta. And we take the two amalgamated sum of these two, which corresponds by the home underlined two functor in the opposite direction to taking the two followed product. So what we get is that we do have a solution, because we have just seen that the two amalgamated sum of topoi does exist. It is a topos. And we get that R alpha plus 1 is equal to R alpha. Can be root construct with R alpha, amalgamated sum. I'm working within delta here. In fact, geometrically it would be a fiber product of topoi. It's much nicer. R alpha, amalgamated sum with rho D tilde over rho S. So that's the construction. Now we still have to check something, namely we have to check that G0 generates alpha plus 1. But generating here means just generating by endomorphism. That's the same thing here in topoi. And that's something transitive. So as G0 generates alpha, all we have to prove is that alpha generates alpha plus 1. Now we have to be, I think, slightly careful in our construction. Yes. Now let's be careful. No, I will give a recipe for, I will give a way of constructing this two-fibered product, which will show that alpha goes to alpha plus 1 is surjective on the objects. Okay. So here again, I have something that is surjective on objects. Essentially surjective, let's call it. It certainly won't be surjective on arrows, because we said I've added arrows. So, I mean, this is not a subtopos of R alpha, definitely not. I have added no new data. It's completely contrary to the intuition of subtopos of sub-theory, which would be correspond to adding exams. But I guess it's surjective on objects. Now let's try to check this. So here we have OS. So let's express R alpha in terms of a site, a subcategory, full subcategory C alpha and R alpha, that is stable under, let's say, finite inverse limits. It's small. Alright, and big enough so that S is contained in C alpha. S was a certain small subset of order R alpha. Alright. And now, how did we get rho D tilde? Maybe I should, maybe we should give a little construction here. What is D tilde first of all? D tilde has as underlying set S. S goes to ob D tilde is surjective. And we have a diagram, you see, and we turn it into category. I mean, the objects of this new category are the vertices of the diagram. They are just some more arrows which you obtain by taking passes, by taking formal composites of arrows. Alright. And now, so this, alrighty, what should we say? What I want to say is, so here we have R alpha plus 1. So what we know already is that alpha plus 1 is generated by the construction we gave of it in terms of small subcategories here and there, you see. It's generated by small subcategories here and there, and of course it's generated by this and by the images of this and that. All right. Now, that's it. Now, R alpha in turn is generated by J naught. Now, all we have to prove is that the image of this here in R alpha plus 1, that every element in the image of this here can be covered by elements of J naught, or amounts to the same because of transitivity of coverings, can be covered by elements of R alpha. Now let's try to see this. How do we get an element of rho d tilde? See, we have to take finite products of objects of d tilde and then direct limits of such things. That's how we did it. Arbitrary direct limits. Now, the objects of d tilde, they come from objects of S. And when we take the products, their images in alpha plus 1, you see, they are the images also in this way. But that's it. But this function here commutes with finite products, you see. These the products that we got here, they come from the products that we have here. And therefore also the right limits that we have to take. In fact, what we can say is the following. I mean, in fact, maybe it's simpler. R alpha plus 1 is already generated by d tilde R alpha and R alpha. And d tilde, you see, consists of finite products of objects of coming from S, and these are the finite products that comes through here. So it is true that here we get something which is surjective, essentially surjective, although it's by no means surjective on arrows. All right, and now fourth step, it's a transfinite induction if you want. Assume that alpha is a limit ordinal, and we have all R betas for beta strictly smaller than alpha already constructed together with I goes to these R betas. And we assume that J naught goes to the R betas, generates all of the R betas, and we took the topos R, and we take the theory, that is the two inverse limits of the series R beta. Of course, this corresponds, as all these series, yeah, that's it, this corresponds by the definition of the two direct limit to taking the serial equivalent by the two direct limit of the R betas that we have already constructed. You see, we constructed it, for instance, by taking the two direct limit of the R betas in the category of categories, and then taking it, but the R betas are a little bit too big for this, so we better take, sides in them, subcaps that are small and that are stable under the transition morphisms. We take the direct limit of this, then we take a subtopos of the row of C where C is this category. And if we take everything finite under finite inverse limits, we can take a subtopos of C hat even. So that's how we constructed this R. So we get actually a topos, so therefore we know again that our theory is representable by a topos, but we still have to check that J naught generates R. But that's, I think, pretty clear by what I have just recalled. If you take this C beta in R beta, then R will be generated by C, which was just the direct limit of the C betas. So R is generated by the images of the C betas in R, and R forced by the images of the R betas in R. And as J naught generates each of the R betas, we again through. So this proves that if I goes to R is basic, if I goes to R, let's say, That's it. Corresponds to an algebraic theory with a basic functor. Then R must be a topos. Of course. Well, of course, no. Yeah. You have to prove it. Really. And the finite products of objects of I generate R, which implies, of course, that R is a topos. All right. And now let's show the opposite direction. We now assume that this condition that we have such a that we have a topos with such a functor. In fact, we should need only say we have such a functor because then R will necessarily be a topos, because then we have the generators, this small family of generators, and we will prove that this situation is algebraic with basic sets. That's all that remains to be proved, of course. We know already that R is algebraic. That's what we saw at the very beginning with basic set I. And so we have to reconstruct, step by step, an algebraic theory in terms of the data. And it will turn out that we can do this really in a very minimal way. In a minimal way, we don't need any transfinite construction, okay? But here we need just take our basic objects, of course, to start with. This step number one is always the same. Second, add arrows between finite products, and then put axioms. That's all. But of course, these axioms are not the same as if you admit ourselves only finite or infinite inverse limits. These axioms, in order to formulate the axioms, for instance, we can formulate as an axiom that certain families of arrows are epimorphic, for instance, and some axioms that involve infinite dicaments, for instance. That's the difference with the more algebraic theories, which we have seen before. And let's prove it. So here we have R, here we have I, so here's the theory TR, and of course this theory TR we will get as an abutment. You see, it will be made into more trivial theories, and we will get it ultimately as a fourth step of a certain construction. So first construction is that we take the empty structure on base sets I, and let's see if you have recalled how this works. Here it's represented, now I will use my little diagram. Let's see, how did I write my nice diagram? We have I, here J naught, which obtained from I by adding finite products to objects parameterized by I, and then here I have R naught, which I can write down as being either J naught hat or as being rho of I, or also it's the envelope to going from categories where finite products exist for this pi to category data of J naught. That's a nice way of expressing it. So we can view R naught as being the topos that is the envelope of the analyzer, J naught. The analyzer is a category, a small category in which finite products exist. So that's various ways of describing it. Now, second step, I will add arrows. And what arrows am I going to add now? All right, here I have the R, you see. And of course, I have R not mapped into R because of our I mapped into R. Unique way. And I look at the induced functor in here. And I will add, to add an object of J naught, I will add all arrows that are between these objects when they look at the images in R. That means that I'm looking at the full subcategory, the J naught defines an R, except that possibly two different elements here give the same element in R. Maybe it's handier not to identify them. So that here I have in fact, all right. Now when I add these arrows, we know already, so, by definition we have still an algebraic theory, we know also how to construct it, we gave the construction. And we can interpret the construction the following way. we first add these arrows to the analyzer J naught. Namely, we keep the same underlying set and we add these arrows, but we still insist that products should remain products. So when we have some arrows, we have other arrows that we can construct tagging Cartesian products, etc. That's kind of nice, I think, to do it this way. Because we see the basic set is just the same. If there was just one base element, for instance, we would just have arrows between powers of a fixed element next to the n. We give, for instance, a composition of x squared equals to x. Right, I mean, in terms of this, we can construct many other arrows. But we keep the same object. And then R1 would be just the pi comma delta envelope of J1. That's one way of expressing it. Alright? Yeah, pi is a category. So two of all categories in which finite products exist. And now, adding axioms. Well, I mean, the first axiom I want to add is that the arrows which I had in J1, that their composition is the composition that we had in R. How should I say this? That's it. There are arrows which I took here. You see, let's take that we have 3 elements A, B, C in J naught. You see, each of them is a product of elements coming from I. And assume, and we have a functor which goes from J naught into R for this phi. So in fact, for every arrow which is between phi A and phi B, I add an arrow. And for every arrow which is between phi B and phi C, I add an arrow. You see? But so I formulate an arrow from A to B and another arrow from B to C. And therefore, when I do this formally, there will be a compositor by the construction of J1. But this compositor, you see, the phi of this compositor will not be, of course, in general, the compositor of these here. So I add these axioms. All right. Now I will come to adding these axioms. I will have here a subtopos R2 of R1 that represents the new theory, which I have by adding these axioms. And we can obtain it in the following way. We take the analyzer that is obtained from J1 by adding these axioms. You see that as I already can write these axioms in J1, so I have still the same objects here. Same objects, same objects. Only here you have more arrows, and here you pass to the quotient on the arrows. And then you take the envelope, the rho pi comma delta envelope of J2. All right. And now, what is the functor that we have represented now? Let's call well, J2 in fact, what should I say? Yes, J2 is a full subset of R generated by J naught. That's how we have constructed it. And what we have been taking now is that for every topos E, the theory that is represented by R2 is the following. For every topos E, we take all functors from J2 to E that are compatible with products. These can be considered as being delta functors from R2 to E. Now J2 generates R because J0, J2 and J0 as objects of consent are the same. And J0 by assumption generates R. And therefore, this from R2, from delta of R2 and E, if we view this as containing, as getting mapped into its own delta RE, you see, here, the theory which we have constructed here, T2 gets of course mapped into it. This theory, T, the theory represented by R. We now know that this here is a full embedding. And in fact, we know which is a full embedding. Then you have to take the functors from J2 into R. That, well, that have the property not only to commute finite products, but that the corresponding functor from R2 into E, you see, well, should be a continuous functor from J2 into E. Then we should transform certain inductive cones. Maybe those cones here that become exact in R, they should become exact in E. So that's a bunch of axioms that you add on it. And then some more axioms, namely that this functor from R2 to E should commute with finite inverse limits and famous enough, as we have seen stated on some small subcategory. Well, I mean, maybe what I say here is not so much needed. After all, what we can say is, yeah, all right. So we see that now this last step here goes directly from R2 to R, that we therefore appears as being R3, adding more axioms, namely the axioms I have just said. And then these two last steps, we have functors of localization. Here we have just passed to quotient by making certain errors invertible, and here again we have made certain errors invertible. Now, when we have twice, you see, made a bunch of errors invertible, you see, we have seen that that the errors which we get here are then surjective on both objects and arrows, you see, they correspond to subtopoi. Then of course we could have done it in a single time. So R3 can be obtained from R1 by just making a bunch of arrows invertible. So that means that we get our theory here with the base objects I, you see, by adding products, putting arrows on the products, writing down some relations of these arrows that are more than the ones I have first contemplated. Certain number of relations that can be expressed by saying that, well, what is R1? Are the elements of R1? Well, after all, now all the elements of R1 become constructions, you see. These are things that we can construct in terms of these finite products and the arrows which have been put among them, you see, by using finite inverse limits and arbitrary like limits. First finite inverse limits and then arbitrary like limits. And using the data, we can put arrows in between them and we write that certain of these arrows become invertible and that's all. Of course, using also the axioms of topoi in order to write down the things. So I was rather painstaking here, you see, because I wanted to make things in detail so that one feels kind of safe.
Isn't the water with the more actions?
Yes.
When you actually change it to J3.
You want to see what are the axioms?
Yeah.
All right. So you see, in fact, we know that yes. So the situation is the following: you have a topos R, you see. You have a subcategory J in R. Turns out here, but that's not so important, that it's stable under finite products. And now you look for every E, you see. You look at the subcategory from delta, from lower delta RE of. We look at this functor, which goes from hom underlined RE to hom underlined of JE. Here, for instance, you may take the functor such with products. It's self-contained, you see, in hom underlined within cut the whole of cut of JE taking all functors. Alright, this we view as being a theory for this tau over pi j, t lower pi j of E, and this we make for this theory t lower cut JE. So this would be this here represented by j within pi, and this is represented by j within cut. This here is a full subcategory, and we assume that j is generating in R, as was the case here. And this implies that this functor here, this goes from here to there, and therefore also the functor that goes from here to there, is fully faithful. And it consists, as we have explained yesterday, it consists of all those functors from j into E that on the one hand are continuous, and second, such that if they are continuous, this means that they can be factored in an essentially unique way into a functor from R into E, and second, that this functor from R to E commutes is left exact. And now I want to show that these two conditions can be written as axioms in the standard way, as axioms that we put on this theory here. So let's make these axioms explicit. Or on this theory, but in fact this theory can be already seen as being deduced from this theory by adding axioms. Namely, when we write that the functor commutes with finite products after all, when that's an axiom. How should I? Maybe it's not quite clear to you. Let's write, for instance, let's write the condition within this theory that an object in here, which is therefore a functor from G to A, E, commutes with finite products. Let's write how this can be written as an axiom in the technical sense of our one of our first discussions of what an axiom should be on a theory. All right. So let's take two objects, X and Y, in J, and the condition we want to write on an object, call it phi in here, we want to write that phi of x times y mapped in the natural way to phi x times phi y is an isomorphism. Alright, we want to show that this condition on the object in here is one axiom in our technical sense. And for this, I noticed that every element of J defines us a construction for this theory simply for T of E if you want. And it's not, perhaps it's not, or S of E, let's say. When we have an element X and J, it will allow us to define for every E a functor from TE into E. There is a functor which associates to every phi in TE the value of phi on X for this functor epsilon X. It's a functor value at X. That is for every object in TE, every structure of type T and E, namely every functor phi from J to E, we associate the limit of E, which depends functionally on it, which is compatible with space change when E varies. So that's a way of associating to a structure of a certain type with an E, an object of E. And on the other hand, this depends completely on X. You see, because phi X depends completely on X. That is, if you have an arrow from X times Y, for instance, into X or into Y by taking the two projections, then we get an arrow which goes from epsilon X times Y into both epsilon X and into epsilon Y. That is, we have morphism between constructions. We have natural homomorphism between these functors. Associating, for instance, to every, what do I know, to every group object in a different way, an object of the category in which this group is being considered. You can consider, for instance, take on the one hand, it's an abelianized group, and on the other hand, you can take, let's say, the group divided, but the center doesn't make sense, but let's say the group itself, and the homomorphism of one into the other, namely the canonical homomorphism of the group into this abelianized group, I mean. And if we write, for instance, that this should be an epimorphism, And then that's an empty axiom. And if you write that's an isomorphism, that would be an axiom, which would mean the tool is commutative, or such things. And now here, you see, what I do have is these two constructions, epsilon x and epsilon y, and epsilon and the third construction, epsilon x times y. In fact, the category J can be considered as being a full subcategory of all constructions. You see, and by associating to every x corresponding epsilon x. And what I want now to write is that epsilon x times y of phi mapped into epsilon x of phi on the one hand and to epsilon y of phi on the other hand, because of these two functional homomorphisms, transforms this into the product of these two. But this means that if you look at the single arrow which goes from epsilon x times y phi into epsilon x phi times epsilon y phi, because of these two arrows, of course I assume that in the category E finite products exist, and in order to be able to write this axiom, I want that this should be an isomorphism. But this also means that if I look at epsilon x times y mapped into epsilon x times epsilon y, this arrow is transformed precisely by this arrow. When we apply it to a given phi, gives precisely this arrow. We want that this arrow should be transformed into an isomorphism. And that's so we have given an arrow between constructions relative to our theory, and we are now demanding that this arrow between constructions should be transformed into an isomorphism by the more specific types of structures that we are considering. And that's the axiom on the structure. I mean, this kind of was underlying our whole setup. You see, that's the way we write down axioms. But throughout, you see, in all this setup, when E was supposed to be a variable object of delta, you see, the categories of constructions are, for this theory were R0, for this theory were R1, for this theory were R2. When a theory is represented by a category R in delta, let's say, working in delta, then the category of constructions you have seen is just R itself. And therefore, you see, writing axioms by saying that certain arrows become invertible, certain arrows between constructions just mean that certain arrows between the elements of, in this case it would be R2, let's say, become invertible. Now here we have existence of the functors that we are considering commutous kernels, and therefore if you want to equalize two arrows, this just means that the arrow from a kernel to a bigger object, to the ended object, should become an isomorphism. So we need only one type of axioms. We need not the equalizing axiom, because it reduces to the axiom of making some arrows isomorphisms, which is kind of nicer to handle. It corresponds to the setup of categories of fractions. Alright, so therefore we see that this subcategory in here, this is just a little side remark, but that's not really our essential point, can be viewed as being deduced from this theory by adding axioms. This here, called this S of E, this here is S prime of E. S prime of E is deduced from S of E by adding axioms. And in the same way, I claim that this category, S second of E, is deduced from S of E by adding still more axioms. So we can say that we first add axioms in order to get S prime and E, and then now we put some more axioms in order to make it still smaller. And now we have to recall what was the situation? What are we going to use of this situation? I have a category J2 contained in the category, in the topos R. I assume that J2, never mind the index, you see, is generating in R. And moreover, all right, but that's rather inessential. I assume that it's stable under finite products. And I want now to show, but forget about the finite products, because we will put the axioms one on here. I think this will be more understandable, because it's kind of irrelevant, these finite products. All right, and I want to consider the theory represented by the category J2 by associating to every E the category of all homomorphisms of J into E. You see, this category gets mapped into it. The theory represented by R, but in the delta sense, from underline delta R E, because when we have a homomorphism from R into E within delta, it restricts to a functor from J2 into E. And now I want, on the other hand, because J is generating an R, we know that this here is a full subcategory. I want to show that this full subcategory can be expressed by axioms. And in fact, that's what I have said an hour or so ago, when I said that when I have a subtopos, you see, this situation just means that R can be viewed as being a subtopos of the enveloping topos of J, which enveloping topos is precisely what we call R2 here, except that in this set R, we took the enveloping topos and we took into account already the products here. Never, that's a little detail, it doesn't really matter. Because this functor, I mean by our general nonsense, this functor here is represented, for value E and delta, is represented by topos, which we call R2. And we had a full subfunctor here, which essentially means that we have a subtopos of R2. But I can make explicit what the axioms are, in fact, very easily. That when the functors, the general theory of topoi gives us that if, call this C perhaps, this would be nicer. It's a generating set with an R, generating capital with an R. So the functor from C into E that correspond to morphism of topoi from R to E are exactly those which are continuous and which are, if things are simple, so that C is stable under finite inverse limits, which moreover are left exact. So let's first assume this. Now let's assert that this can be written as being axioms. In fact, what does now, that means that if family xi goes to y within C is epimorphic in R2, if it's covering for the topology on C induced by R, then if this is covering, we should show that we should then demand that phi xi goes to phi of y should be covering. Now I want to write this down in the canonical form, as meaning that a certain arrow between constructions becomes an isomorphism. All right. Now the category of constructions is just R2. And what I do is to take, first I take the direct sum of the xi's within R2, if you want. And I write this arrow from the sum of the xi's into y, and I should write that it becomes covering. But that an arrow becomes covering within a topos can be expressed in terms of another arrow becoming an isomorphism, if you want. Because, as we have seen, it just means that the arrow here being, what do I know, being alpha, if you want. This means that the diagram here, that this square is co-Cartesian, or it just means that the diagram, that the arrow which goes from the amalgamated sum of y plus y under x to y is an isomorphism. So what we finally do is the following. I look at the following arrow within R2. It is y amalgamated sum with y over the direct sum of the xi's goes into y. This here can be viewed as being a homomorphism between constructions. It's a homomorphism in R2. And I restrict to those delta functors from R2 into E, I mean to those objects of TE which were interpreted as delta functors from R2 into E, turn this arrow into an isomorphism, or what amount to the same. I look at those objects of TE that when we apply to this object this construction and this construction, and the arrow between them, it becomes an isomorphism. I mean, when you think a little about it, all this becomes completely logical. It's a little like algebraic geometry, with all these functors. It's tautological, but you have to get used to it. Yeah. After, I mean, that's, maybe we have to So I think that's, so to say, the general story about within topoi. You see algebraic structures that make a sense within topoi. If you view them as being algebraic structures in topoi, if you define the morphism between them, insofar as they make sense as morphisms for structures of this type realized in topoi, these algebraic structures can be just identified with topoi. What is nice, however, is that when you look at the topoi in a geometric way, rather, you see, then the arrows between the series, of course, go in the same direction as the arrows between the topoi, and not in the opposite direction. And so every type of algebraic structure that practically all types of algebraic structures that have been considered, you see, that one likes to call algebraic, with the exception of the other, it shouldn't involve infinite products, you see, this is no such thing, infinite inverse limits. This would be bad, but if it's only type of inverse limits that are being considered are finite inverse limits, and then really most things are work all right for topoi. And so I mean the yoga is that algebraic structures are topoi.
Yeah,
That's it. The given algebraic structure is to the topos. Of course, this would be qualified in various ways. You see, I kind of pointed out or marked something about some type of axioms would not be axioms in our sense here. I could perhaps give a particular case of the empty structure on one object. I think this is perhaps kind of illuminating. And looking up all substructures, for instance. That means that what are all the axioms you can put on one object, unspecified object of the topos, without giving any error. And that would be it. So that's what's the universal. I mean, that's what the classifying topoi are for, in order to do things universally. So let's look up a little bit here. Yes. So the structure type that you're envisioning is empty on one base object. Alright, so what is the classifying topos? As we call it. So I is just one set. We have to add finite products. I is just one point. We have to take formally, this one point stands for one unspecified object in a topos. And we have to add products, take the set of all xn's, and the maps between the xn's come from projections and nothing more. N is equal to 0, cause category J. The maps between the xn's here come from the projections. In fact, the category of the xn's is opposite, is equivalent to the category opposite to category of finite sets, including the 0 set. And the classifying topos here is being had. Therefore, it's the category of all confluent functors from J to sets, or the functor of all covariant functors from finite sets to sets, and that's what are called post-simplicial sets, except that they have to be augmented. Equal, augmented, post-simplicial sets. Objects of this topos, I think, have a highly non-trivial homology, by the way. Of course, the final object has trivial homology. That's true for other algebraic structures. This here is and the like structure in the strictest sense defined by finite inverse limits. And such structures have always trivial converging. But other objects, I mean, co-simplicial sets are just, I mean, as intricate, as rich, I think, as simplicial sets. All right, so it's a nice types of objects, but that's not what we're concerned in. And now, what are the points of this topos? Points? Well, quite generally, perhaps we should say that if we have a classifying topos for a theory, that B is a topos classifying for a theory T, we call it B lower T. For instance, B lower groups would be the classifying topos for groups, etc. So then we see that the category of points of B lower T is a category by definition of homomorphisms of topoi of the one point topos, call it P, into Bt, and by definition of the classifying topos, this is T of R's naught. And therefore, if you take the opposite of the category of points, this would be the category of fiber functors over Bt. This is just T of R's. Maybe we make a little remark that in all of the categories T of E, which would be from lower delta of Bt and E, which would be also from top opposite Bt. You see, in these categories, filtering diagonals exist because the properties of exactness on the functor, namely commuting with filtering with arbitrary diagonals and finite inverse limits, this property is exact, is stable under filtering diagonals because in the topos, finite inverse limits commute with filtering diagonals. So they have filtering diagonals, and that's all kind of diagonals. And that's all one can say, I think. I think there's no other type of limit that exists in all of these categories TE, that exists in any category from top EB. All right. So therefore, we might expect to get pretty large categories as category of points, you see, because they will be still under diagonals. And of course, points, the category of points, therefore, is stable under inverse limits, filtering inverse limits. Has filtering inverse limits. So points of our classifying topos B, that's just the opposite category of the set-theoretic realizations of our structure, namely of R's. That's R's naught. And fiber functors on B, that's therefore just a category of sets. But the fiber functors that you are really interested in, that are the most important, are those that are finite representation, or that's also that correspond to essential points, that correspond to fiber functors that commute also with arbitrary products. So this contains as a subcategory the category of finite sets. Maybe finite sets, we can give it a name phi, or something like this. And in fact, this is end of finite sets, so it can be constructed through finite sets. So the points you are really interested in are the points delta naught, delta 1, delta n, which are the functors represented by those xn's if I consider this classifying topos as being j tilde. It's fantastic. Well, by the points of j, which I call also xn. Sometimes I call them delta n or things of them as being standard simplices. And it turns out, in this particular case, that subtopoi are already defined, already known when we know the points they contain. In fact, the closure, so to say, of their points. For an arbitrary topos, you see, when you take a bunch of points, you can take the smallest subtopos that contains these points by taking as which corresponds to those arrows within the topos. So we have to make some arrows invertible. Corresponds to those arrows, such that the fibers of these arrows at the given points should become isomorphisms. So in this way, we have a way of obtaining certain subtopoi, and in some cases, and the most important subtopoi, which I have met so far, they can be obtained this way. So this is, in fact, in our case here, all subtopoi can be obtained in this way, and I will give you the result. I will give you the whole diagram of implications. Call this classifying topos B. Now you remember that to give a subtopos of a topos which is of the type J hat, say, is the same thing as to give an arbitrary topology on J. So what we are classifying are the topologies on J. And by this interpretation, it's kind of, should I say, it's just an exercise. You just do it. You just look at the axioms for topology. Here, in fact, in J, fiber products exist, so topologies can be viewed as being pre-topologies. It's the same thing, essentially. And one just looks, and here's the diagram. I have to copy it, otherwise I may mix it up. You have, on the one hand, the topos B, then you have just one open subtopos, B star. The open subtopoi corresponds to all subobjects of the final object. We have always the whole subtopos, of course, and the empty subtopos, which are two open subtopoi. Here there is another one, and I will say on another diagram what it corresponds to. This corresponds to the, I will tell you what its finite points are. These here will be the points. I will write underneath them, underneath the topoi, perhaps the subtopoi, I will write the points. Here, if B corresponds to all integers, let's say, its finite points are all delta n's. Here would we have all n's that are different from 0 and star. I will give the interpretation in terms of theories in a minute. All right. Then we have, so these are the only open subtopoi that correspond to subobjects of the final object, and I will tell you what the subobjects are. I have the universal object X here of the topos, and here I have the final object, and this here, interpreted in terms of a subobject of the final object, would be the image of X over EB. So we have here we have the, how do you call it? The structure map, call it F, and this would be the image of F. So there's just, in terms of one object in a topos, there are just three sub-objects that one can define canonically of the final object. Namely, the empty one, EB, there's no merit for this, and then the image of X. That's what it says. All right, now whenever we have an open subtopos, there's a closed complement which is being constructed in the nodes. And this closed complement, the points are those that don't belong to the open ones. So here, this closed complement, I give it a name here. Never mind. I called it phi naught. So it will just correspond to the unique point delta naught. So I'm sorry if I interpret everything in terms of sets of integers. it would be just the 0 element in n. So that's the complement of n star. All right. Now, in terms of, let's say these subtopics to which sub-series they correspond. So the big theory was T of E, let's call it T over B of E, is equal to the whole of E, giving an arbitrary object in E. So recall that X is the canonical object in a topos, and therefore if you have any topos E, to get an object in the topos is the same thing as to get a morphism of E into Vt, and the object in E, or this, how do I call it, a small x if you want. X is just the inverse image of this object here. And therefore, I have this, the correspondence between subtopoi and sub-series is that if I have a subtopos, I look at all morphisms from E into Vt that factors through the subtopos and at the inverse images of the universal object here. And I look and see what objects I obtain here. So here I had no restriction on the object. Now here T over V star. I now want that this morphism of E into Vt should factor through the image of X in the final object. That means that if I look at the inverse image, this should become that small x goes to small t should be epimorphic. So Tv star of E equals the set of all objects X in E such that X goes to the final object is epimorphic. So here it's the axiom of being an epimorphism. The structural morphism is an epimorphism. What's the name of our? Here we have F if you want, and here the kind of structural morphism from X into the final object of E called phi. Something like this. All right. What is in fact, in terms of set-centric realizations, you see what are the sets that correspond to the subtopo, to this thing. These are the sets such that structural morphism of the set to a one-point set. It's epimorphic. That means that's the non-empty sets, and that's what I wrote down by putting in n star here and we are restricting finite sets. All right. Whereas here I take the subtopos having just one point, the point having how many elements now? It corresponds, point. Having 0 elements. So, that's it, yes. All right. And the sub-theory here corresponds, of course, here I have the empty topos, to which let's first look at this empty topos. What's the sub-theory? So B2 should take all morphisms of topoi from E into Vt that factors through the empty subtopos, but such a morphism exists if and only if E itself is an empty topos. Therefore, the sub-theory we have here is that T of E is equal to empty set if E is non-empty and to just one element if E is empty. So that's. And now here, what does correspond to this here? T of E will be reduced to just one point. T of E will be the set of all x's in E such that x is an initial object. Namely such that, if you want, empty index E goes to X could be an isomorphism. And we're looking in the category of sets, that means that we take empty sets. There's just one empty set, it turns out in the set. But the category T of E, you see, is equivalent to the 1 point category. All the objects here are equivalent. Isomorphic, I'm sorry. All right. And now there are two more intermediate things. Here we have phi naught 1 here, which is a unique subtopos having exactly the points, as finite points, having exactly the points naught and 1. So the sets of realizations correspond to sets that have at most naught or 1 point. That means that the structural morphism from this into 1 point set is a monomorphism. And that's the general description. T lower phi naught 1 E. Here it would be T lower phi naught E. And here T lower empty E. Equals the set of all subobjects of the final object. It's a nice functor, by the way. Yeah? We will look a little bit more closely to this topos, which has just 2 points, but which is not a discrete topos. And moreover, we have the intersection of these two, whose points are the intersection of the points here and the points there. So it's just, we have just the point 1. Phi naught 1 intersects B star, and now, how would we call this? Phi 1, I would think, yes. Call this Phi 1. So its finite points are just finite point 1. What is a set-zoetic realization? It's sets that have exactly 1 point. At least if we take finite sets, but the same description would apply to arbitrary sets. That means that the structure morphism to the final object is an isomorphism. But here, in fact, we have said that the structure morphism should be an epimorphism. Here we have said that it should be a monomorphism. When we add the two, it means that it's an isomorphism. So this here is just T phi 1 T equals set of all final. Of all final is the category, I'm sorry, of all final objects of E, which is again, of course, equal to the 1 point category. So we see that these two topoi, phi 1 and phi naught, they're just these two topoi. They are just the 1 point topos. They are the final topos. But of course, so they're just to correspond to 2 points within Vn, but of course these 2 points are not the same. So this here is isomorphic to 1 point topos, this is isomorphic to 1 point topos, because to every E I'm associated with a category which is just equivalent to the 1 point category. This here is the empty topos, so all these are all, these three are all friends of ours. This here is a topos which would correspond, I think, to co-simplifical sets, not two augmented ones. As a category, you see, this would just correspond to covariant functors going from non-empty finite sets to an arbitrary topos. There's here augmented co-simplifical sets again. Of course, as categories here we get R's, here we get R's, here we get 1 point category, and here we will see in a minute. This one we have already investigated. Now this here just corresponds to what I could call delta 1 hat, where delta 1 is the following category. It has two objects and just one arrow in between them. And delta 1 hat, therefore, is a category of concurrent functors from these two sets. That is the category of pairs of sets and the map between them. Now, is this, that's it, yes. Now, of course, to give any functor from delta n, delta 1, into a category E, for instance, a topos, is the same thing as to give two objects of the topos x and y, and to give an arrow in between them. That's it. And therefore, to give any continuous functor from delta 1 tilde into E is the same thing as to give such an arrow in E. So continuous functors are just arrows between objects. But now, what are the continuous functors that are left exact? Namely, that correspond to morphism of topoi in the opposite direction. Of course, I don't know which of these two objects, in fact, is the final object. It's this one here. You see, delta 1 is a final object, and therefore it will be a final object in delta 1 hat, and therefore it should be transformed into the final object of E. Therefore, a necessary condition already should be that the target should be the final object of E. And on the other hand, this one arrow, because there's just one, is a monomorphism, and therefore it remains a monomorphism in delta 1 hat by the canonical inclusion, and therefore it should be transformed into a monomorphism. And therefore a necessary condition for a functor here to come from a morphism of topoi here is that this should be an injective map, a monomorphism. And it's easy to check that the converse holds true too. Now you remark that this topos here is in fact of the top of a topological space. It's in fact a topological space. This equals top of, let's call again delta 1. Let's call also as a topological space which has just 2 points, one of them being closed. I am sure I can't remember which one, and the other not being closed, the other being open, in fact, and having this first point in its closure. It's a spectrum of a discrete validation of topological space. So we have a very nice topological space, such to give a morphism of a topos into this topological space is the same thing as to give an open subset of the topos to a subobject of the final object. And in fact, this topological space is a cogenerator in some sense, I don't remember exactly which, in the two category of those topoi in which the subobject of the final object form a set of generators. That's those which resemble topological spaces, let's say. They are slightly more general than topological spaces. They may not have any points, for instance. Any topological space, for instance, can be embedded into a product of copies of delta 1, even if this topological space is not separated. It's something that for not necessarily separated spaces replaces, you see, the real line or the torus for compact spaces. It's a really nice space that we see sitting in here. So that's a perfectly good theory, you see, associating parallel topos, all open subsets of the topos, as presented by this topological space. All right, and of course this diagram shows how these subtopoi intersect, of course. Subtopoi they form just labeled under. In fact, they form a lattice. There are arbitrary intersections and arbitrary soups. and here the diagram shows exactly how the story is. Now, I think it would be very good for health system already to get a better understanding of how topoi look like and how universal constructions can be performed, to look at a few more examples. So here I looked at the example of just one object without extra structure. We could look at just two objects without extra structure. See, and the classifying topos for this, I think it would be kind of nice. Of course, we have all subtopoids that come from X and all subtopoids that come from Y. And then you can take 8 intersections of these, you see you have already what they generate. But I think that probably if you have something more, you see, because after all, now you can look at products of X and Y and ask things about them. So, for instance, what about asking this X times Y is empty? Something like this. Is this? No, this is. Well, no, anyhow. I think that probably here again, if you have only a finite number of subtopoids, I would suspect. You can also look at, given an arrow from X into a Y, what are all axioms that one can put, you see, on such a situation. Two objects and arrows from X to Y. Of course, you have on one conditions that you can put on X already, or conditions that you can put on Y, or conditions that you can put on the pair X, Y. But then also conditions that involve the arrow between them. I think this kind of look at this kind of problem, I think, would be a good way of getting acquainted with topoi. And then, as something perhaps slightly more sophisticated, an object and an anamorphism of an object. All these are algebraic structures in the simplest sense, maybe. I think they can be described in terms of nothing, not even products. But then let's look at the next step, a composition law between three sets, X and Y goes into Z. What kind of axioms what kind of subtopoi of the classifying topos, in other words, what are the subseries of this tree that you can obtain by maybe putting some axioms? Is there an infinite number of things? Maybe only a finite number here. You see, because you can't compose these things within itself. You don't have much structure. If already you assume that you have X which operates on Y instead of in Y, perhaps you have a little more. And then, of course, if now you have a composition law on X, now it gets, I think, that you get something very rich. You have groups and all kinds of. So this is probably, well, I kind of suspect that there are too many subtopoi to have really a good hold on all of them. So you would just write down some little diagram here. Maybe we make a little break, small only. And I want to say goodbye to two people around here. And then we will see afterwards what we do.
Maybe we can recap.
Huh?
Can we recap?
Hmm?
Can we recapitulate?
Maybe yes. Yeah. From any point you want.
0.
Maybe it would be better
But
if
do you
somebody
have
of you chaps went to the blackboard and started recapitulating, because you see, otherwise, I just not.
I'd like some more examples myself.
Yes.
Yeah, I can give you a few examples and then we recapitulate. Spend half an hour giving more examples. I want to. Maybe we can figure out somewhere. Oh, yeah. Let's see. All right. So, I mean, anyhow, this need not be a trouble for us right now.
Could we, what's the, let's see, look at the classifying topos for a group.
Yeah. So,
Now what's the, could you go through the same thing both ways with it, starting from the other way around?
I mean, for groups, I mean, it's so trivial that one doesn't
Okay.
have any.
Good.
If it's just to find the classifying topos to see in explicit terms, that's the easiest thing in the world. So, all right, take the category of groups for finite presentation. Call this S, or sigma if you want, something like this, and call small r if you want the opposite category. And then you admit, I guess, that this, if you are interested in categories that have finite inverse limits and functor commuting with these, then inside of R there sits the universal group, and in fact the universal group is just Z, you see, and we, in fact, in order to give it a group structure within small r, it's the same as to give it a co-group structure within sigma. So we have to map Z into the free product of Z by itself. It's just a sum in the category, and this is done by mapping, I guess, the generator 1 into E of the right hand. EE. Yeah. E1, E2, let's say. Let's see, E1 the generator of Z and E2 the generator of this vector Z, and we take. Now we have to dissociate them and E here is the one generator. So generator E here, 1 and 2. E1, E2. And then one checks that this is the universal co-group. Or in the opposite category, it's a universal group. Alright, and now the classifying topos is R equals small r hat. Why is this? Because take a topos E and look at group structures in E, so we have admitted that they just correspond to functors from R into E that are left exact and that commute, and that's all, that left exact functors from R to E. Now, functors from R to E just correspond to functors from R has to E that commute with arbitrary direct limits, and the functor here is left exactly from all here. This functor is left exact. And that's part of the general story I told you about morphisms of topoi defined by a site into an arbitrary topos. Morphism, delta morphism, let's say, morphisms of topoi components of the line. And therefore, in the opposite direction, we have a morphism of topoi of E into R. The notations are really unfortunate, should be known by the same letter. The cut of sheet on the topos and the topos. Maybe you should really distinguish them. So then it goes there. If X is the topos defined by E, so that E are sheet on X, and B is the topos defined by R, the classifying topos of our structure, below and below. This means that we come out like this. Alright, now this is about groups. And now, of course, commutative groups correspond to the subtopos by writing university accent away. Some arrows inverted.
Okay, how about the classifying topos VG for a single group in G sets?
Yeah, this is. It's kind of a nice question. You see, when you have a category, C, what is our algebraic structure of which the topos C hat is a classifying topos? I mean, it's kind of subtle sometimes. We have seen, for instance, it's maybe less expected. So this means then E is a topos, what are the functors from C into E such that their unique extension as a continuous functor from C hat to E, is left exact. When C has already defined inverse limits, this means that it takes left exact functors. There's no problems, no mystery. But in other cases, I think the situations sometimes turn out to be kind of subtle. Because the left exactness property, you see, it's kind of funny. It's a property which is kind of on C hat, it looks like a pure algebraic, in the stricter sense, algebraic condition. I mean, it involves only inverse limits. Now, in the case when C was the category which I have described here, the category delta 1, two objects and just one arrow between them, and then the identities. Then you see functors from C into E are just arrows between objects of E, and the condition that the functor here corresponds to morphism of topoi. A delta morphism here, that means the morphism of topoi is opposite direction, means that Y is a final object, and that the morphism here is a monomorphism. Now this is the way it can be expressed, so inverse limits. But now let's take another example. Let's take for C the category with just one object and G and the endomorphism of this object forming a group G. Then a functor from C into E is just an object X of E together with an operation of G on this object. So, and therefore continuous functors from C hat to E, they are just represented by such things. And of course, what are the corresponding continuous functors? Well, I mean, we have the object, call it, how do we say? I want to say what is the correspondence. C hat here is just precisely VG, the category of sets on which G operates. That's it. And I now have to say what is a functor that is associated to from C hat into E that can be expressed through an object X of E on which G operates. Let's be specific. So let's the variable object in here, let's call it, but we know P, let's say, that P be a variable object in VG, that's a set on which G operates. Alright? And to P I will associate P contracted product by Gx, which is defined to be the following thing. It's obtained by taking P times X, so to say the constant object of this value P and E times X. That means the sum of capital P copies, the direct sum of capital P copies of X. And then dividing it out by the action of G operating diagonally. In fact, when we let it operate, well, let's see, functors here, G equals on the left, all right? We take complement functors to sets, so we should have G operate on P on the right. And so here, I would let G operate on this by P comma X, G operating on it is equal to PG G minus 1x. So in other words, I want to identify PGX should be equivalent to P comma GX. So G should be able to pass from left to the right. And that's a well-known construction of the contracted product. So in this way, associating to every object X on which G operates, associating this functor, see, we get we get an equivalence of categories between these objects with operators and functors from C into E that commute with direct limits. All right, and now the question is, what is the condition on X for such a functor to be left exact? It turns out that the condition is that that X should be a torsor under the constant group object G lower E. So in such a way that we see that the algebraic structure represented by this topos C hat is the algebraic structure of a G torsor over variable topoi. Now, this, in fact, this story is a pretty useful story which works with
Is this supposed to be running?
Yeah.
Oh, it's running.
Yeah.
So let S be any topos, and let, so the category of sheaves, perhaps we should distinguish between the two. The category of sheaves of S, call it, what do I know? Call it something like B. And over S, I have a group object, G, instead of given B, let's say. And now I want to represent the following theory, which lies over the theory already represented by S, you see. For every topos, call it X, you see, I look at the category of all morphisms on X into S. So I'm restricting, so to say, to X is lying over S. That means I'm looking at a theory which should lie over the theory already represented by S, together with a torsor on X under the inverse image of the group G on X. So for every X I look at the categories. If you prefer, perhaps it's simpler to visualize it by taking the category of all topoi lying over S. So that's another two category. It makes a sense for every theory to look at the category of topoi X together with an object and T of X where T is a theory. Yeah, therefore, then to define the functions accordingly respecting this object. All right. For instance, if S is a classifying topos for rings, this would mean that we are looking at ring topoi. Topoi lying over the topos, classifying topos of rings is just topoi endowed with a sheaf of rings. All right. And I look for every such topos X lying over S, I look at the category, which I may call, what I know, T, now lower G of X, but lower G is fixed. It's the category of torsors over X with respect to the inverse image of G. And I look at this for variable X. And I want to represent it. What does it mean to represent this? This would mean to find a particular topos S prime lying over S with a particular torsor P prime under the group G lower S prime, inverse image of G on S prime. So G S prime operating on P prime on the right. In such a way that for every X lying over S, the canonical morphism which goes from hom top XS to torsors over X under the group GX, which associates to every homomorphism of topoi the inverse image by the homomorphism. I'm sorry, but I am taking, of course, the S homomorphisms which are compatible with projections on S, which associate to this F upper star of P prime, which will be the inverse image of a torsor is a torsor, so it will be a torsor under the inverse image of GS prime on X, namely, which is also the inverse image of G on X directly by this arrow. See? So this is in fact a contrail functor, so it's a functor like this. should be an equivalence of categories. So that's the universal problem. So this would be what we would call the universal G-torsor. And I will give, in a little while, I will give a few interesting examples. It's insanity to have such universal torsors. And they have been used a number of times already to reduce, you see, because the universal topoi that one is constructing, you see, they may have some very nice features like being Euclidean or looking Euclidean and such things, and one may be able to do molecular algebra better. And things that we want to prove in the general case, we reduce it to the universal case. In the universal case, it can work better because the topoi are so simple, they're so completely explicit underhand. For instance, some things about Chern classes have been checked in this way, in Chern classes for crystal homology or such things. All right, now I will give the construction, which is just, the generalization. In fact, when S is just the one-point topos, then G is just a usual group. Then what we found was the classifying topos of G, the so-called classifying topos of G, which was the topos such as the sheaves on this topos were sets on which G operates. And we have explained the construction. I didn't prove the theorem which I stated here, that this functor here is left exact if and only if X is a torsor. But one is, I guess, we're willing to admit it. It's not hard to prove something. I think it's given in my Tohoku paper already. The meaning of torsors, I think, was explained. Not Tohoku, I'm sorry. There's a Kansas paper on sheaves with structures, on parameters with structures. All right, now let me give the construction here. In fact, it turns out that S prime, the category of sheaves over S prime, will be the category of objects of B, sheaves over S, on which the sheaf G operates. On the left, preferably. So just the same construction as when we were working in sets. And that the topos is pretty trivial. You just check the properties. The exact properties that are true in B will be true in BG because the functor, the forgetful functor which goes from BG to B, you see, operating the branches of G, is of course faithful, and it commutes with all operations. So operations you see of G, they once you, if you have objects xi on which G operates, sheaves xi on which G operates. If you make any diagonal inverse limits on these sheaves, Gi you see, G will still operate on the limits, so the limits are just constructed. First in B and then the operation of G carry over. So this functor commutes with space when it commutes with any type of limits, and therefore the exactness properties which you want to check here, it's enough to check them there. B is a topos. But of course we have also the generator. All this is pretty clear. All right. So it is a topos. It's something exceedingly explicit here. And now I will, in this topos, I will construct a torsor under the inverse image of G. So we should say what is the inverse image of G. Yeah, I should say what is the projection of S prime to S. So such a morphism should correspond to morphism in the opposite direction, having all nice exact properties, which goes to a functor which goes from B into BG, the inverse image functor. And this functor, as we will take it here, called this morphism here P. So this would be the functor P upper star which we have to describe. It associates to every object X in B the same X with trivial operations of G. Both types of these arrows, the forgetting arrow or putting trivial operations, is a particular case of a functor which corresponds to morphism of group objects. Then we have a functor BG prime goes to BG, which associates to every sheaf on which G prime operates, the same sheaf but in which we restrict the operations to G. This functor commutes with all limits. And therefore it's a morphism of topoi, it's even an essential morphism. corresponds to north of topoi, but it goes in the opposite direction of north of topoi. Alright, so we have this here. And therefore, the inverse image of the group is just the same group, but viewed as having GS operating on it in a trivial way. Huh? That's pretty clear. And now I want to describe a torsor under this group. So a torsor under, so this group here, you have G here, and the inverse image in VG, we will call inverse images by an upper bar if you want. So this is just G with trivial operations. And the same, of course, composition law as before. And now, to define, we have to define an object in here and then operations of G bar on this object. And an object in here, we have first to define the object in V and then the operations. And now what we will take as object in here, and in here is G itself. Alright. And now we will have to say, in order that we explain an object here, in fact, we will have to have G operate on G on the left. And I will take GS. I will take G operating on G by left translations. So I will take P, the universal torsor we're looking for. I call this P prime here, by the way. Why not? I will take for this G lower S. Lower S means that we put operators on it with left translations. And now I have to give an operation of G bar on P prime on the right. I have to define P prime times G bar goes to P prime. Now for this I have to define it for the underlying objects of V and then check that it commutes with operations. So the underlying objects in V, what are they? They are GS and G and GS. So I have to map GS times G into GS. In fact, GS, I mean they are G, G and G. But I will let the subscript S. Maybe here. And alright, how will I define this? Well, that's just this composition law of G. That means G operates on GS by right translations. If I view it as G operating on GS, you see, by right translations now. Before I had made it operate by left translation. Now I have it operate by right translation. It's the right task I'm looking for. It is clear? But of course we have to check the axioms. I mean, we have first to check that this really is a morphism in here, that it commutes with the action of G on these three factors. Then G acts on this factor trivially, and on these two factors by left translations. But this comes from the fact that left translations commute with right translations. Alright, so we have really an arrow in here. And I claim that in this arrow, P prime becomes a torsor under G bar. So we have associativity, etc. And also that it's a torsor. I mean that it's a true torsor and that P bar, the P prime covers the final object. But because our functor here is faithful and exact, we have only to prove that after we apply this functor, we get a torsor. But it's pretty clear that GS is a torsor under G, operating by right translations, right torsor. Alright. So of course this torsor is trivial when viewed in V. It has a section, but it doesn't have an invariant section. You see. It's not trivial when you view it in S prime because their sections mean invariant sections. But it's pretty hard to have a section of GS that is invariant, a section that is invariant by which translations it would be? By left translations, you see. This is the point. All right. I am a little confused, however, my middle boy. Because our torsor that he has constructed has a special property. Namely, you see this functor corresponds to a section of S prime, of the topos S prime over S. And apparently, when we take the inverse image of this torsor by this section, then we find a trivial torsor. No, it is not an external prime. No, but this section has no. So what? No, that doesn't disturb us. That's all right. Fine. So I got the torsor here, and now I have to prove that this is universal. Now let's see in down to earth terms what this means. So let's first see. Yeah. So let's write down the diagram for inverse image functors that correspond to this situation. We have B goes to Bg by B star. Then X corresponds, let's say, to a category of sheaves E. So X lying over S, this means that B is mapped into E, call this your Q if you want, so this could be Q alpha star. Our group G is inside of B. Yeah. How will we get it? We want to make an interpretation as in the sense of the case. What's this statement? I want to prove that to give a torsor an E under the inverse image of G, a right torsor is the same thing as to give a functor like this that has the right exactness properties and that makes the triangle commutative up to given isomorphism. Alright, now let's first express what it means to give an object X and E on which the inverse image of G operates. I claim that this is the same thing as a functor from Bg into E commuting with arbitrary like limits. And the relation between the two is expressed in the following way. If we have our X, then we associate to this the functor, but maybe our notations are not the same as there. The notation we get a little bit mixed up. So G operates on the left, on this X, no, on the right, let's say, rather. On the other hand, we get an object in Vg, an object in V, on which G operates, which is variable. So it's an object of Vg. Call this object Y. See? And we take the constructed product of X times 2 star Y, contracted product with respect to the action of the group G that operates on the right on X and which operates on the left on 2 star Y. So I should perhaps rather call it V lower E, its inverse image by 2 star. It's the image by 2 star of G. And so for variable Y, I get a functor with respect to Y. And this functor, you see, in fact, it's a compositum of Vg goes to B, to B lower Ge, you see? So every object with operations in B associated with in E, which is observations in E with operations by the group Ge, and then I take the contracted product in E. Mostly in these arguments one takes B equals to E, you see, the base change then. And one shows that torsors under D correspond to sections of B, if you would. So that's the way of getting it. So one has to check something here, but I think it's kind of trivial. I'm not sure I would get it out so easily because getting played.
Do you have any other examples offhand that are this is quite a striking example.
Yeah.
No, the G sets in the case here, or in more general cases, this algebraic structure that's being classified by that it's representing is that of torsors.
What's the question of?
No, nothing. I just find this a striking example. Do you have any other?
Yes, because here you see
Because-
the condition for to be a torsor is something kind of subtle. You see.
Yes, and then
Whereas it's really, you just take all the topos that you have constructed is just a C hat with
Oh, that's what I
very
meant.
silly down to earth C.
that's what I.
One can of course set out now to look at a number of pretty easy categories. But if a G is a monoid, by the way, I don't know too well.
I doubt if this is true, is it?
That doesn't exist, I think, the notion of a
Well,
torsor and a monoid, does it?
well, you can make something that accomplishes the same thing, but not quite as
I didn't try
not quite
to
as
see.
handy.
It might be interesting to see what it is. If G is a monoid, what is the algebraic structure represented by a G hat? I don't know. Let me give one or two examples to see where this is kind of handy. Assume that we're interested on the variable ring space, or local ring space. Never mind. Look, what doesn't make a difference? Ring space, but commutatively ring space. To looking at modules that are locally free of finite type, or of a given rank, let's say, locally free of a given rank n. Given rank n. So for variable ring spaces, I mean, this is silly. X sits over specifying topos for commutative rings. All right, and we are often in the case, I mean, to want to make some constructions which these things construct all kind of relative group schemes with respect to this, or construct in terms of such a datum, construct homology objects, homology classes, characteristic classes of such a bundle, for instance, the Scherm classes and such things. You see when we are lucky. And in order to make such kind of constructions, you sometimes you don't see at all how to do it unless you go over to the universal case. And so I will tell you what the universal case is. And when we say that OX is locally free of rank n, that means that locally that the sheaf we are looking at is locally free of rank n. That means that locally on the topos x, it is isomorphic to x to the n. But when we have over a site or a topos, when you have a fibered category, you see, which is, as we say, a stack, namely that not only the morphisms but also the objects can be grouped together. In other words, when with respect to this fibered category, any epimorphic family of morphisms within the topos or within the site is of 2%, and that's the case here, you see. In topos, I mean everything relative objects, and together with arbitrary kinds of structures that they can be always grouped together. You see? If you have such a thing, then the classification of when we have a given section of such a stack over X, and we have a given object associated to the final object, then the classification of all those objects that are locally isomorphic to this one is done by torsors under the sheaf of automorphisms. We have in fact an equivalence of categories between the category of all sections of our stack that are locally isomorphic to the given section one, here it would be 2x to the n, and the category of torsors under the sheaf of automorphisms of 4x to the n. In this case. To a torsor, we use a torsor, so to say, to twist the given object in order to make it into a locally isomorphic one. All right. Now, the group of automorphisms of OXN, that's the sheaf G and N OX. All right. So we are interested in fact, giving an E the same thing as to give such a torsor under this group. On the other hand, this torsor we can already find in the universal case. For instance, that's it. To say that X has a sheaf of rings means that X lies over the classifying topos per ring that in fact is Schach finite presentation hat. We look at the category of all affine schemes of finite type over Z, and we look at the category of all pre-sheaves over this. And within this category there is a ring which associates to every scheme, affine scheme of finite type over the integers, its ring. Or if you look at things as being covariant functors from rings to sets, it's a functor which associates to every ring the underlying set. That's the universal ring. As a universal ring in a topos, that's this one. Alright? So to give X as a ring space is just to give a morphism from X into ring here. And now our group sheaf GL, the universal one, we have it here in fact. GL N with respect to the universal ring. So if I would take in our example here S to be topos for the universal ring, and here I take G to be the full linear group over this ring, the sheaf. And therefore, to give an invertible, a locally free sheaf of rank n on X is the same thing as to give a torsor on X under the inverse condition of the sheaf of groups. And therefore, we can find a universal such thing, and we take reclassifying topos Vg of S. Over this we have the universal torsor under G, and in fact under the inverse condition of G, to be more accurate. And to this torsor is associated a locally free sheaf of rank 1 on Vg. And that's it. Now this Vg is something exceedingly explicit. If X, in fact, if the sheaf of rings here is a sheaf of local rings, this just means that X can be factored through a certain subtopos, which will be essentially the same, associated to the same category here, except that we have to change the topology. Instead of taking the chaotic topology, we'll take the Zariski topology on it. And then we will take here, so therefore the topos of Zariski sheaves on this category of affine schemes of finite type over Z. And if we wanted that our sheaf of rings should be Henselian, you see, not only local but strictly local, so which is somewhat stronger property, just as local rings they can do this stronger condition than for ring to be local. Demanding that, well, there's a Hensel condition. Never mind, it's a technical condition that describes the right geometry. And then this just means that you put that this factors with still a smaller subtopos, which is obtained by taking a still stronger topology, higher topology on this same category, namely the topology, the état topology. So according to, of course, according to the kind of requirements you may put on the building, you are, I mean, this universal ground scheme for rings becomes, ground topos for rings becomes smaller and smaller, and the corresponding universal topos for locally free rings of locally free sheaves of rank n, of course, becomes smaller also. So according to the kind of problem you have to deal with when you go working with one or the other of these things. Let's give another example of a problem where certain type of algebraic structure can be reduced to topos. Let X be a topos corresponding to a sheaf, to a cluster of sheaves E, and assume we are interested in objects of X of E, so sheaves over X, that are locally constant. Now, I mean, this is an axiom that makes sense in the theory of topos. I mean, it's something that can be written down using just the fact that the topos is an object of the topos. However, it's easy to see that this cannot be expressed, you see, by a subtopos of the empty structure. In fact, we have already said what is the subtopos. I mean, it doesn't correspond, associating to every, in other words, associating to every topos E, the category T of E, the full subcategory of E of all locally constant objects. You get in this way a theory, but this theory is not presentable. It's not algebraic. This comes from, just we can see, for instance, by logic, that locally constant objects, they are not stable under taking direct limits. It would be, of course, in the category of sets, everything is locally constant, but not in the category. For instance, when you take a totally disconnected topological space, for instance, then a direct limit of sheaves over it that are locally constant will not be locally constant. For connected spaces, over locally connected spaces, it would be so, I guess, but not in general. On the other hand, you may also write down other conditions for I. For instance, I is locally constant of order n. That's the covering of order n of the final object. Just a nice italic covering, a covering. That means that locally it's isomorphic to the constant object with n elements. Now this is still more evident that it cannot be written down as an algebraic theory, because in the category of sets, you see, the sets with n elements are not stable under direct limits. You see, if you take direct limits of sets, filtering direct limit of sets of cardinal at most n is of cardinal n is of cardinal at most n, but it can be of cardinal 1, for instance. You can keep sending all things in the same point, you see. So, and however, I mean, this is a very interesting kind of object to consider in a topos. I mean, étale coverings, finite retrieval possibly, of the final object. I mean, they give rise to the theory of the fundamental group, etc. They are very important objects to consider. Now, you can do it in the following way. You can say that if you, of course, let's take finite coverings, for instance, and why not just restrict to those which are given order n? Because if the order was not specified, X would decompose into the sum of topoi, such as on each of these orders is a given one. So let's just give the order beforehand. But then it's the same story as before. What are what are these objects in E? That are those which are locally isomorphic to the constant object of value In, where In is a standard set with n elements, the set of, let's say, the first n integers. And therefore, if we look at the sheaf of automorphisms of In, this of course will be the constant sheaf of groups whose value is a symmetric group in n letters. And therefore, the category of all these i's will be equivalent to the category of torsors under this group Sn, but be careful when I say the category of all these objects, which will be these objects taking only isomorphisms between them and homomorphisms. The same restriction I should have made, by the way, when I was speaking of locally free sheaves. You see. The category of locally free sheaves of rank n on a given ring topos is equivalent to the category of torsors under the full linear group in letters, provided we take only isomorphisms between locally free sheaves of rank n. So we are losing something. So we are representing, if you want, another theory, you see, where the categories are not the same at all. They have the same objects, but they don't have the same homomorphisms. So provided we make this, when we cut down on the morphisms, then we can represent the new theory. But of course, it's pretty much different one. So here it's just the same thing. So therefore, here in fact, we have to take the classifying topos of Sn, where here Sn in fact is viewed as being a group over on the one point on the topos, on the final topos. And therefore in fact here the universal topos endowed with a locally constant object of rank n is just the classifying topos Bsn of all sets, such that the category of Schilon are the sets on which the group Sn operates. For instance, if you take commutative rings, let's say, and then the fact that the spectrum is connected can be expressed as a property of the ring that makes a sense in any topos. So we can express it by saying, for instance, that if you have two idempotents in the ring that are orthogonal to each other and whose sum is equal to 1, then one must be equal to 0 and the other must be equal to 1. That's the true algebraic way of formulating these, of formulating the condition. So connected rings, so to say, the rings whose spectrum is connected. The theory of these, makes a sense in all topoi. It corresponds, in fact, to a certain subtopos, which can be nicely described, of the classifying topos for all commutative rings, which I have written on the blackboard. But now what about rings such that the spectrum has exactly n connected components, or finite number of connected components? Now this doesn't correspond to a theory, because again this property is not stable under passage to filtering like limits, neither of them. But one can, however, restrict the theory by taking for every topos V. One can define on the other hand this notion. If you have a ring in a topos, you will say that it has exactly n components, which can be written as a product of rings, of exactly n rings, which are not zero and that are connected, that are zero connected, let's call it. You see, and this decomposition can be easily shown to be unique in this case. It's complete canonical. So here again we have a notion that can be described in terms of a topos, but which doesn't correspond to axioms in quotes, in the sense we have explained them, to standard types of axioms. So for variable topos, although this notion we have also is perfectly compatible with inverse images, taking inverse images by morphism of topoi, you see. However, the corresponding theory which we get is by no means representable, and still less is it algebraic. And so, however, can we find something universal? And the answer is again yes. But we can find something universal in the how should I say, in the modified sense, when we take as morphisms between rings A and B in a topos A, E, when A and B are rings which have exactly n connected components. In the sense I have said, not in the sense that A is an object of E when I forget about my structure and connected components. That's not what I mean. The ring A can be decomposed into product of n rings that are zero connected in the same form. Alright. I will take as homomorphisms between A and B, and only those which, of course, such a homomorphism will induce a homomorphism from what I would call pi naught A and pi naught B, namely the set of indices which enter in the decomposition of A into a product and the decomposition of B into a product. Pi naught, perhaps let's put an upper exclamation mark, because it's not the pi naught of A just as an object with our structure in E, but it's the pi naught when you take into account the ring structure. So it will become something like the pi naught of the spectrum ring. Alright. And let's now restrict to those homomorphisms of rings for this here is an isomorphism between the pi naughts. And then I claim that for this new theory, where I take as category T of E, the category of all rings in E having the property I stated, and as homomorphism between those which has this extra property stated, this now will be representative. And I tell you how. The story is kind of nice, because I will express in an alternative way what is this to give a ring. I'm sorry, when I said that the ring had only n connected components, I said it's a ring that can be written as a product. That was unaccurate. That can be written locally as a product. That's what will be the correct description. The set of indices you see yes, is defined only locally, and in fact as a discrete set, you see. But what is really defined is a twisted object, which is of rank n, you see. So, in fact, what the correct definition would be, I mean, one has to analyze a little bit the situation, you see. But what really comes out after analyzing the situation is the following, that in a topos E in which the final object is E, see? So let X be the topos E is a couple of sheaves, small e is final object of it, so we sometimes kind of like to identify in X. Ring with pi naught, a ring that has locally n-connected components, would be obtained in the following way. We give ourselves an n-shielded covering X prime of the topos X, beta covering, which just would mean the same thing as to give ourselves an object, call it y naught I over E, that is locally constant of rank n. And we give ourselves a ring over I, you see, call this A naught if you want, over I. This would be something like the generic connected component of the ring that you are going to construct, A naught over I, which is connected as a ring in the induced topos E over I, namely we give ourselves, if you prefer to say it this way, a ring A naught in the topos X prime, a sheaf of rings A naught over X prime. Not yet. Not yet. A catastrophe. So A naught is zero connected as a ring. So it means that the spectrum, so to say, is everywhere connected non-empty. And on the other hand, the ring A I'm considering can be written with F star of A naught. Let's say the functor which goes from the category of these pair of objects, an object I over E that is locally constant of rank n over E, and the ring A naught over I that is zero connected. The functor which goes from this category to the category of rings in of sheaves of rings on X by associating to such a pair the direct image by this morphism of the sheaf of rings A naught is fully faithful when we take a morphism between these rings. no, is fully faithful, then we take isomorphism between the rings downstairs, between rings A and B, those which induce locally isomorphisms on the pi norms. So if a ring can be written down in this way, you see, then this covering I of E of the final object and this ring A naught are determined up to unique isomorphism. So you have a way of restating what it means if you have a ring that is, as I have exactly n geometric connected, that has exactly n connected components in a way. Relative and locally, so to say, relatively to the basis x. If the topos x has enough points, this would just mean that all stalks, which of this ring that are just usual commutative rings, have spectra which have exactly n connected components. So that's the condition. So if there are enough points, it's kind of easy to express. And so the catalog of these rings, when we take isomorphisms between them, those which induce, for at every stalk, let's say, an isomorphism between the pi naughts of the spectra, you see, this category can be expressed as a category of such coverings, n-sheeted coverings of an object, n-sheeted unrelated coverings, plus a ring over I that is now zero connected over I, which has the property that all stalks will be non-zero rings whose spectrum is connected. All right. And now such rings, I mean, for such things we have a universal way of getting them. There's a universal one, because there's a universal locally constant object of rank n over E, provided that we take only isomorphisms between the objects, and that's precisely what the restriction almost of rings corresponded to, because this I stands for the set of indices, you see, for the pi naught. And on the other hand, over a given topos there's also a universal ring, you see, which is a product of this topos and the topos for the universal ring in the absolute sense. Therefore, what we have to take in fact is, let's see, is this so? Yes, now let's construct the universal topos for, let's say, how would you call them? For, how would we call these rings that have this pi naught where nobody is n? Well, so that means that locally there are exactly n mutually n mutually orthogonal idempotents whose sum is equal to 1, and this cannot be any further subdivided. So we'll call them n rings, something like that. Right. Now, how will we construct the universal n ring? And the classifying topos for this? Right, first consider the classifying topos for locally constant objects. So that's B lower Sn on by. And now, therefore, to give a ring of the type we want in a topos X, amounts first of all to map X into this topos. Because that means that we give us now in X on X such a n-shielded covering. And now I have to express, once I have already this arrow, I have to express that I give myself a ring on this inverse image. That's it. Now I have here the universal I, you see. Call this I, a fat I, lower n. That's the universal n-fold covering, beta covering. And now, that's it. And in fact, what I'm interested now is in all possible ways for a given arrow here, you see, to give a ring which is now connected, zero connected. On this topos, given object, call it I. Never mind which topos, which object, shouldn't matter at all. And now we want to construct, in a universal way, a topos B prime over B, and over I prime a ring of A prime, where I prime is the inverse image of I and B prime. We want to do this universally. And now the solution should be trivial, but what is it? Now to give a ring over I prime is just the same thing as to give a morphism of I prime into the classifying topos for rings, call it something like R or so. Therefore, in geometrical terms, I have to give let's write the things geometrically. You see this I view as being a topos. It's a line over V. It's an n-folded, n-sheeted covering. Yes, and so if I will V prime, I look at the effective of objects. I'm getting stuck now.
With magic.
It's time to
The canonical.
Let's see. Ring or anything else, of course. I mean, some kind of structure you see. Well, what is it, for instance, if you have it on I? So it's the same thing as a B-morphism from I to R times B. So I think what we are what you want to write down is something which would be called the topos from underline within top lower B of I and R times B, which I call R lower B in order to indicate that it lies lower B. So in fact here it seems that we have Why did I get stuck? You see, it's because I don't have any nice way apparently ready. You see, to express this classifying topos. That the classifying topos exists is kind of evident, of course, because I have already an algebraic theory, the one I'm represented by B. I have an object with an algebraic theory, and then to give a ring over this object, I mean, as again, in the commutative ring is again, of course, to add just one more object, I mean, to have the heads into the, you could have thought of this object as being hidden in your pocket while we are constructing the theory B and never involving arrows or axioms with this object, and then all of a sudden you take it out of your pocket, and then you put some arrows involving it, an arrow, for instance, from A times I A into A, which is a composition law, and then another one, which would be addition, and you put bunches of axioms on them. So that's an algebraic structure, it's pretty clear, so that it has a classifying topos. It's pretty clear too. So this was the main point I wanted to make, in fact, except that I wanted to have it kind of pretty, but I just don't get it out. If I is constant object, you see, is a constant object of rank n, then of course this should be RB to the n, yes. Then to give it, of course, then to give a ring over the sum of n copies of the final object is just the same thing as to give n rings. see. And therefore, I mean, the classifying topos then would be Rn times B, where R is classifying topos for rings. But if I is a general object, so this has something to do with understanding how these topos look like. And I haven't even thought about the existence of.
Does that exist? Do you feel that intuitively it does exist?
I don't know. I met one or two cases where they existed, and then I asked myself the question, but I didn't.
What were those
sit down.
cases? Do you remember what those cases were?
I think there were delta n's or such things. Okay. So some small categories, so that's a home of delta n's. There isn't something happen to exist. Just I didn't think yet of God's existence. Maybe it's trivial, I don't know. In fact, before one sits down and does the things, you see, one sometimes feels, you see, a little afraid of the things. For instance, we made a big mess in SGA about inverse limits of topoi. And of course, I mean, this mess, I think, is an inheritance from the times when we were afraid of all of these canonical isomorphisms, etc. And so we were very painstaking, etc. And being so painstaking with respect to technical details, which in fact are kind of irrelevant in a way, for the intuition of the thing, we finally lose track of the fundamentally simple situation. And then we think that the existence of inverse limits is a non-trivial matter, even in the filtering case. That's a wholly trivial matter in the completely general case. I mean, I gave the construction that it was nothing. So, and maybe it's the same thing with, I don't know, maybe this is
Just look at it, I have to look at it right.
And look it up, I don't know. Now, the formalism of topoi is so extremely smooth, you see. It's funny, some things, it's something special about topoi, however, I must say. They are really brilliant. Every once in a while, I think, well, after all, these kind of, this or that property must hold for more or less arbitrary categories. For instance, let's say that I just recently looked up this case. We have a category C and another category E. We assume, let's say, E is a topos. That's it. Let's say, I mean, that will be really essential in fact. And C, let's say, also has finite inverse limits. No, let's assume only that in E arbitrary direct limits exist. Let's say in finite inverse limits, which would be the case for a topos. And in this case, because of arbitrary direct limits exist, functors from C to E correspond in one-to-one way to functors from C hat into E that commute with arbitrary direct limits. And now, when E is a topos, it turns out that functors here are left exact if and only if the extension is left exact. And so a few days ago I said, well, I mean, that's silly, and that's not because it's a topos really, and it should always be true. Well, and what I then checked is that assuming, for instance, that E has a small strictly generating subcategory, that then for this property to be true, for this given C assuming that it's stable under finite inverse limits, of course, and then, now I assume also that E is stable under finite inverse limits. For this statement to hold true in this, particular situation, it's necessary and sufficient that E should be a topos. And I mean, it's pretty easy to see, because if C is strictly generating, this means that the functor which goes from E into C hat is fully faithful. And then, of course, the functor which goes from C hat to E is left adjoint. And if this left adjoint is left exactly the topos. So you see it, and just it. And now this statement about interpreting the homomorphism from C hat into E that are both continuous and left exact as being the arbitrary functions from C into E that are left exact. I mean, it's played a key role in our interpretation in our construction of classifying topoi. So really, I think that you can get this construction of classifying topoi in such a really amazingly simple way. Although it's a mixed case, you see, when you have both types of limits, both inverse and like limits, it really comes from the fact that the axioms are so exceedingly well fitted, you see. I guess if you take, for instance, something which might look simpler because you have only a finite number of, you have only a small number of operations, namely if you take abelian categories, take the enveloping abelian category of one object, let's say. I don't think it's easy to visualize, you see. I think I can construct it, I guess, by transfinite construction, but you just don't see really the objects. I think the construction has to be transfinite. You keep adding, you see, kernels and topos and such things. But here you see our classifying topoi, and you always got them in a small number of steps. And that kind of explicit. Now I think in order really to feel at ease with these things, one should compute out in one's own sphere, you see, of interest, which may be abelian groups, which may be schemes, which may be commutative rings, therefore, which may be anything you like, if you have anything, some kind of algebraic structure which you kind of are familiar with. If you write down the classifying topos for this kind of algebraic structure, and then you look at all kind of axioms and see at the subtopoi how they fit together, and it's kind of pleasant. The kind of question one might ask, for instance, is all possible ways to decompose classifying topos into a, let's say, for instance, the connected components of the classifying topos are kind of nice. This would correspond to in how many ways can one decompose a topos carrying a certain type of structure, using this kind of structure, etc. Most classifying topos that one meets, I think, spontaneously they are connected. For instance, if you take classifying topos for an algebraic structure in the strict sense, defined by finite inverse limits, this is acyclic in all limits. It's cohomology with values in any. In fact, it's cohomology with values in any sheaf of commutative groups. It's zero. So you don't get much cohomology invariance. I guess it must be true also that the H1 is values in non-commutative sheaf is zero. So these kind of elements you won't get for such very simple kind of stuff. When we were discussing in the class the other day, we spoke about subfunctional identity functor.
Right.
You see, I mean, when you look at these things for topoi associating to every abelian group and topos and abelian subgroup, you see, and this kind of in a functorial way compatible with inverse limits. This just corresponds to taking all subgroups of the universal abelian group. So look at the classifying topos for abelian groups. I mean, it's something pretty explicit, quite explicit even. And on this you have an abelian sheaf, and then you look at all the abelian subsheaf, and that's it. So it kinds of gives you a kind of trivial reduction of problems that you might wish to ask. And sometimes it may be useful. But we spoke about making a revision kind of how should I say? I mean, giving a maybe
Well,
bird eyes view of what we already got or did not get so far.
yes, maybe we could write it down without any proofs, just maybe, like sometimes they have these little cards that you can carry in your notebook of, the essential facts of music or something. It's all on one page.
She does audio now.
Or calculus, all the differentiation rules.
Maybe somebody else should go to the blackboard and may resume. Maybe this would make more sense. No, it's not good enough to be qualified, but I mean, explaining what you understood so far and seeing what the comments of the others are. You don't feel like it?
No, absolutely not.
Yes, please. Yeah.
I think Jack is probably understands more than the rest of us on that.
Maybe why don't you go to the blackboard and tell us what you think of this kind of story, what you understand and what is not clear to you. And that's
I
not
really, this is the last time, I'd really prefer to sit back and think about it myself before I try to start it out, and verbally recapitulate. That was my goal.
well, blackboard may help, of course. You see.
The general notion is to take a category satisfying, first of all, define the notion of exactness condition. What do you mean by a category satisfying exactness condition? And functor satisfying, preserving exactness condition. This gives our category delta.
Now for the functors, we were pretty crude, you see, just
Right.
commuting to certain types of limits.
Oh yes, okay, you treat that's,
Yeah.
Well, I miss a lot of this stuff, but I'm curious about one point. When Lawvere or here he emphasized certain differences with this Grothendieck approach. What is? Because I have the idea that topos have shields on sides. Sides are kind of realization of topological spaces, but then I left this. But I know that there is another approach. What is the main difference?
I think you just want to know the difference between
well,
Lawvere's
there's
definition of
elementary topo,
With the Lawvere.
Lawvere are just ones that you can define. The definition that they use are just functors that have categories that were Cartesian closed. There was a Hom underlined, which was right adjoint to the Cartesian product, to product actually, category of product. Well, product of two objects. So the thing acts like sets in the sense that you've got a function space which is right adjoint to the Cartesian product as a function. And that condition, plus you had an object which played the same role which classified subobjects of any given object. And that's the definition of an elementary topo, set those two things up functorially. And then there's a theorem that if you add nothing, plus finite limits. And see, what do we tell you? If you add, let's see, if you add more limits, if you add limits as needed, plus generators, and you've got a topos in the sense of zero. That's the relationship between the two. And those are very powerful pair of axes, those two subobjects, and it's Cartesian closed. You can really derive a fantastic amount of things start falling out. As you start imitating construction, you've got finite inverse limits. So you start imitating construction, you have sets. So you start constructing things. And you construct your quotient, literally, and start imitating what you do in sets, things like that. You can always do that. Pick out.
Quotient by the functors represent, by the consonant functors represent?
Yeah, it's just
Well, that's a kind of nice thing. You see, quotients are defined by the coherent functors that represent. And they are defined. But in fact, in topo use, when you have the right exactness properties, you can also directly describe the consonant functor that represent. I mean, that I did on the blackboard in the last action, on the right university. And that's quite often, I mean, the best way to construct the quotient if you want to have it really with strong properties. Yeah. Of course, here in the setup of universal algebra, as I was proposing, we don't work at all with home underline. You see, these functors, these inverse image functors between topoi never commute like with the home underlines. So we can't use them. And in fact, there are very natural axioms one can put on situations that involve the home underlines. I think I said so. For instance, assume that a group G or even a set G operates on an object, G operates on an object X, everything is in a topos. So the fact that G operates faithfully, you see, is not an algebraic axiom in our technical sense, and in fact, it can't possibly be, I mean, that's uploaded here, because it's not stable under taking inverse images. Even if G operates faithfully on X in a topos, when we take the inverse image on another topos lying over the previous one, the action may no longer be faithful. And we are very much restricted. So the mere fact that we said we have a theory, you see, even this much already. It's namely that when B lies over B prime, then TB prime goes to TB by a functor, you see. This is very strong already. It seems to me that definitely topological spaces, this type of structure, cannot be expressed. I don't know how to express.
There's no way, there's no way that you express the notion of whatever, that hasn't been defined. I don't know of anyone, except for Isbell, who has the notion of, topological, the category of topological spaces within a given category.
Well, it doesn't seem too much. I tried to, I fiddled around for half an hour or so. But you see what it would mean in topological space within the topos. It didn't seem to come out at all. Nothing reasonable seemed to come out.
But in his formalism, for example, there is an easy way to interpret it. He has a very strong duality principle, and A and a B is a B and an A. This holds in a very formal sense. So, that, for example, a group in the category, a topological space in the category of groups, through this formal duality becomes for example, just a topological group, a group in topological spaces.
But then I would like to know the definition here, because I'm a little doubtful about what was this.
But he has very strong theory and notions that I would suggest he would be a better one to explain it.
You don't know what the topological space within a category then is.
In this sense, well, it's the thing where he's got.
Can you give a full definition of the category?
No, I couldn't. Not formally, except in this way. Except that it works out so that that's, for example, that's such a thing. He can, in his formalism, you see, he permits easily, for example, all operations that one wants, of all arbitrary cardinalities. For example, something the functors involved that we find here, are strongly non-accessible and even are allowed to go outside of the universe in question. And on this level, it seems to be you can make everything into almost like an operation.
I'd like to see what it is.
See, he's not around. I saw him about an hour ago walking outside of the box.
Well, he might be here.
He was doing his preparing strictly.
Well, I could ask him to come and explain
Yeah,
if he's here.
Well, maybe it's built a bit. Universal algebra.
I'm quite willing, I'm not no longer concerned so much to see, let's say, right now, with whether things can be expressed within this framework. But just, take even a topos, a really good.
Well, no,
I wouldn't know a reasonable notion of a topological space within the topos.
But what you have in the topos, you've got, let me give you one that would work.
What's his office?
For example, take for example, you have the topos.
Would the fibers
You have this.
I find out.
No, you don't. You have the space. For example,
I thought I saw him later.
you have the object, the power set object, that sheet that represents,
Yeah.
this sub-object sheet.
Right.
Okay, so why not, and take a definition on that, an endo, take it, and then you have all of the structure on that object too. It's natural structure. Okay, so do it,
That's what I find.
and that doesn't, well, it doesn't give you anything into it?
Doesn't seem so.
I thought Lawvere explained.
I had the impression, you see, that whatever I could write down, you see, it wouldn't commute with inverse limits of. You see, because
Okay, oh, no, that's interesting. That might not be, that might not.
with inverse images, right? You see, it involved, I think, the operations, for instance, would involve at some places taking infinite intersections of such things.
Yes,
And
that's-
of course,
that's-
models of topos don't commute to this.
And then do morphisms of tuple carry this power set objects in the power set?
No, of course it doesn't.
They do not.
So, I mean, there's a technical error between the P of the one and the inverse image of the P of the other, yeah.
That's
So
right.
it's and it was quite frustrating. It doesn't seem to, nothing seemed to make really good sense. Of course, one can give a definition, but it doesn't seem to be any.
I don't think that that's the definition that he has in mind. It's quite a general. For example, his types of structure can be defined by means of whole systems of whole universes of projective cones, for example. His structure, for example.
Well, those mine were going beyond one universe and getting into the other first.
No, I know.
Depends on the context, you see. One can get a nice note, squeeze a nice note from all of it.
But I don't know, for example, if one of his requirements, in his view, isn't all that, for example, is to go beyond the limits and things like that. I don't think, for example, what he would call his theory, I doubt seriously what he's in any way, what he would call the theory of topological spaces, or he could talk about models of that in some category, would be a pseudo-functor on any reasonable choice of delta.
What would it,
I mean, I just don't think.
what would then be?
Oh, wait a minute, no, I'm sorry, no, but not if the functors are required to, you see in delta, are required to preserve limits, too. I don't think
Would there be anything like a universal topological space?
But he has, on his, for example, his structure and his models, his theories. The theory is correspondent to the models of that theory in some sense. And this he wants into a genuine structure semantics duality, or Lawvere, but only after two steps rather than one.
But he defines structures without caring whether they can be realized anywhere, in any kind of whatever. And he can define the structure, he can construct something like an algebra of structures, independent of any support to these structures. That's.
No, I think they have support. And it's.
But then functors from a cohort category to another should carry, or some types of functors should carry topological spaces in C, into topological space in C prime, I guess.
But I think they in general, provided you've got certain, for example, I can think of cases that certainly they do, because if all you have to do is think about this duality, okay? In his formula, you will have exactly that sort of duality. So that when you're talking about topological space in groups, okay, you're just talking about topological group.
Yeah, but that's not the definition. I mean, that's.
I know that's not the definition, but you can't. There is some.
You mean that if you have a topological one group, it defines your topological memory. But that's no, that's not.
I wouldn't be the best one to explain his structure. His structure semantics.
One thing I may point out is that contrary to what happens with structures that can be defined by inverse limits, the structures that are associated to topoi, they are by no means determined by their set-theoretic representatives, by their set-theoretic realizations. But it's quite possible that they have no set-theoretic realization whatever, also the theory is by no means empty. I mean, and
Well,
otherwise
you just mean T of Rs might be empty.
Yeah, T of Rs might be empty, although the theory is by no means empty. I mean, a theory, if you consider that an algebraic theory just corresponds to a topos, that means that you have a topos without points, but which is not empty. And in fact,
There are those.
there are lots of those.
What's an example of
Is there
those?
an easy example?
Well, the first one that was given was by the linear, and he took, let's see, he took a space with a measure on it, for instance, interval 0, 1, and the Berg measure on it, and he takes as a side all measurable subsets up to sets of measure 0. And as covering families, the families that are covering in the sense of L1 or L1 topology, let's say. That means that there's a countable subfamily such whose union is everything except for a set of measure 0. You see, so that defines your topology, and then it's easy to see that you don't have any points for this. Beside, of course, the topology is coarser than canonical ones, so the side is contained in the topos, so the topos as a full subcategory, so the topos is not, as a category, is not a one-point category. I mean, it's a pretty big thing.
You ought to call those theories ghosts.
Oh, that's good. You see? Well, it sets that kind of point, but I should say points, of course.
No, but you think of algebraic theories as always coming, at least intuitively coming from.
But then
Yeah.
But that's not what you said.
you wind up, well, in the exercise, let's see. What did I say?
You didn't say that you had algebraic theories that had algebraic theories.
Oh no, algebraic is
Yeah.
on the contrary. I mean, the algebraic one in the
Algebraic
strict
is
sense.
exactly in the strict sense.
If you take algebraic ones,
That's-
associates can be defined by inverse limits, no, of course. They are completely characterized.
by
by
them,
theorems. But here, I mean, we have other theories which involve some indirect limits, etc.
We didn't get into that at all, really, in the mixed case, except as in topo.
Yeah.
And there, we really didn't discuss what you could. There we had any direct limits with the things that already existed in the category delta, in the pseudo topo. Did we discuss at any point anything other than algebraic theories in topo?
Any theories? I have.
No, I know they're most defined. No, but we've characterized algebraic theories. Oh, but any topo, wait, right. No, I'm confused.
I think you are. You see, when I say algebraic theories, in the technical sense of the seminar, this meant that could be constructed by stepwise construction I have
Started
indicated.
off, yes.
And I mean, the standard theorem for various deltas should be that the algebraic series are those that are representable by certain objects of delta, which are in a way small enough which can be generated by a small category by adding all the limits that our delta involve. All right? And but the stepwise construction, you see, I mean, it could involve arbitrary direct limits and finite inverse limits in the case when we took for delta pseudo topology. For instance, the structure of coalgebras, comodules, etc. is of course allowed. So it's not the standard algebraic structures where we allow ourselves only inverse limits for defining the structure.
Oh, that's right. Okay, good.
Already, I mean, the example I gave of torsors.
Okay, that's good. Did you do the one for Felix?
Yeah.
And what does it turn out to do?
Yeah, I can tell you. I will tell you what the classifying topos is. It's very nice for fields. You take you take affine schemes of finite type over C, right? And now you add some more covering families. In fact, whenever you have a scheme, then you decompose it into the sum of an open subset and the closed complement. You see? Well, this should be a covering family. On the one hand, you throw out the nilpotence. If you have a morphism which is a closed surjective immersion, it's viewed as being an isomorphism. You neglect already nilpotence. So let's say that your side you can as well take it as being reduced schemes. And on the other hand, when a reduced scheme is cut into two pieces like this, or n pieces, I mean by stepwise construction, it's viewed as being the sum of these. And that's essentially it. But what you wind up with, you can also express in the following way. Let's look. Didn't I explain to you the construction? To every scheme, you can associate a locally compact scheme, which will be this. If X is a scheme, we call it X cons. You see, it's a locally compact schemes, locally compact scheme, in which the open sets are just arbitrary union of constructible sets, and the closed sets are arbitrary intersections of constructible sets. It's locally compact. And if you start with an affine scheme, or more generally quasi-compact and quasi-separated scheme, the corresponding compact scheme, which we can associate to it, is compact. The underlying set, in fact, is the same. It has the same points, but the topology has just been changed. Of course, also the sheet of rings has been greatly changed. In fact, the stalks of the different points, they are just the residue fields. I will tell you how you can construct explicitly the same when you start with a commutative ring, let's say. Then the associated, or if the scheme is queried, I said that the corresponding compact scheme will be affine. But let's see what we do when we start with something affine. All right, we have our affine scheme X, and we look at all possible decompositions of X into n constructible pieces, so n pieces that are locally closed if you want. Now for each such decomposition, we look at the functions on these n pieces, which we can endow with a reduced structure. So we get, for each such decomposition, a ring, which is the product of n rings. And for finite decompositions, we get in this way a direct system of functions, of rings of functions. These functions we may call the constructible functions, you see. They are not the regular functions, but much weaker constructible functions. And when we take the direct limit of all these rings, we get a ring whose spectrum is compact. And you see the transition, in fact, the spectrum is the inverse limit of the spectrum of the intermediate rings, that is the inverse limit of the schemes which you obtain by replacing our scheme by the disjoint sum of the n pieces. We've cut it in two. But the transition morphisms are bijected, you see. And therefore, I mean, passing at the limit, you get still a bijection of the limit to the thing. And it turns out, you see, that the open to enclosed sets are those which I said. Therefore, if you are only, let's say this category is a category of, call it, schemes where we take, let's say all the other schemes, but as morphisms, you take only the constructible things. See, I mean, you take, that's much more general than just ordinary morphisms. All right. So that's the new category you're working with. It's essentially affine scheme of finite type over the integers, but we take constructible morphisms between them instead of taking much more strict morphisms. All right. And now your topos is the following. It's the complement functors. I mean, I will tell you what are the sheet on this topos. It's the complement functors going from these compact schemes to sets that transform, what should I say? Yeah, that transforms sums into products as well. And of course, the universal ring in this topos is the functor, complement functor, which associates to every one of such schemes. I mean, this ring of functions. Now these rings, I mean, they're called in some Ruberti exercises the totally flat rings. You see, there are also the rings, except that we have a finiteness condition over Z. You see, they should be such like they should come from a ring of finite type over Z by this limiting information. But except for this, if you don't make this exercise, there are the rings, such that every module over these rings is flat. There are also the reduced rings whose spectrum is compact, or the reduced rings whose spectrum is separated, etc. But here, so you see, in a way, the universal field, it's in fact this functor which associates to every one of these funny contact totally disconnected spaces is ring of functions. So it's really one of the most extreme cases. In a quite analogous way, you can construct the universal algebraic closed field and, and such things. So in these notes, I give really a lot of examples. Universal normal ring, universal connected ring, universal local ring.
Flat modules and algebraic. Or flat modules over a fixed ring algebraic.
I think so, but I think so. I will give you this description by axioms. I think I can do it. Yes. That means, you see, yeah, let me write it down. Most finiteness conditions, of course, in general are not algebraic. They don't stay with the limits. Like that. If I mode M over A, at least for set-theoretic modules, the criterion of flatness I'm going to give is a known one. I don't know if it works in topoi, because in topoi there is already a notion of flatness of modules, you see. And I don't know if this one is algebraic. It's a pretty good one though. Something which is not trivial, which was proved by the linear, is that it's compatible with inverse images. It's kind of bimorphisms of topoi. It's kind of delicate result. And I guess it must be the right notion. And probably the criterion I'm going to give will be true for this. I didn't check. But it is that for every ideal J and A, finitely generated, that's important in order that we can assert that it's an algebraic axiom, finitely generated ideal. The functor, how should we say? Yes. The map which goes from M tensor J into M, this M tensor, the inclusion map, is injected. Now I will show you that this can be viewed as being as countable number of algebraic, making invertible and countable number of arrows. All right, and for this to when we say finitely generated in A, of course, not only in A, but also over every, when we take it over every object. You see, when we take the induced, the complete definition would be for every object of the topos or the site, let's say also object, but U, and we look at AU, and if you look at the induced sheaf, and if we look at an ideal J in AU, which is generated by a finite number of sections over this U, J equals sigma Fi AU, where the Fi are elements are sections of AU over U, then this here should be true. When we replace, of course, again M by M lower U in order that this should make a sense. Now what is, so in fact for every J I can say also for every system of N sections of A over U, that means for every system of N morphisms from U into A. That's what it means. But there's a universal system of N sections. It's by taking U equals to A to the N. You see? So in fact what we will take is to take A to the N. Alright. Now we have A, let's call this UN. We have A lower UN, which is A to the N plus 1. In fact, you see that's the restriction. It's a product of A by UN. U just being a ring over UN. Now in here we have the N projections.
I'm sorry, well, I mean, we have this, yeah, we have the n projections of an to a, which we can do as sections of a lower u n over this here, call them f1 up to fn if you want, and perhaps, well, I should perhaps put a superscript n also, because, but let's say n is being fixed for the time being. We want to express the axiom here, or given n, let's say, and then we take the conjunction of all these axioms. All right, so we look at these fi's, and I look now at the quotient of AUN by the ideal generated by the fi's, or no, not, I shouldn't say this, I look at the j, lower n, which is sigma fi AUN, which is an ideal within AUN. And I look now at isomorphism from M lower UN tensor Jn into A lower UN. And the axiom is that this becomes that this is an isomorphism model. And that's the property that you have in mind, and this should be true for every n. Because why does this? Why this is of course necessary, because we have just in a particular case we have forgiven and we have expressed this in a particular case, but of course then we have expressed in this particular case, as this particular case is a universal one, we get it always, because if we have these sections of n sections of A over U, this corresponds to morphism like this, and the ideal J generated by these n sections is just the inverse. The ideal J within AU is just the inverse image of the ideal Jn, which we have in AUN generated by the n universal sections, because taking ideals generated by sections is compared to these inverse images. And on the other hand, taking tensor products is also compared with inverse images. And if something was a monomorphism up here, then taking the inverse image is also a monomorphism. All right. And now this here, I mean, is clearly, you see, this is an arrow that we have constructed canonically in terms of your structure A, in terms of your commutative ring A in the topos. So in fact, it's the inverse image of the same thing that you write down in the universal situation. So that's as you go after. Of course, you have to check that these conditions do imply flatness, as is usually defined in terms of the exactness of the functor. So it's known in the topos ans. I guess it should be true.
It is true.
I have not checked. In the topos ans, it's a well-known fact. Yes, it's a Bourbaki, I'm sure. Flatness, you see, can be, yeah, I mean,
Suppose you write it in different ways. Suppose you have two different constructions of the same object in mind.
of which same object?
You mean that agree on ours?
Yeah, they agree on ours.
I mean, of course.
The
When you have a
same-
certain notion,
yeah.
like flatness or so, or connectedness of a ring, etc., you have first to think that there are several candidates that may come to your mind of how to extend this notion in the general case. And sometimes both may be good, I don't know, and they may be different. And sometimes one, after thinking, for instance, one may not be stable under inverse images. By the opposite of topos, and you just discard it. So far I have not met with a situation of serious doubt, you see. All the notions I have met with, I just saw one reasonable way of extending. Hey, but didn't Madame Akin? Hey, yes, she had but that was for relative schemes. In the case of flat presentation, she had troubles with flatness. She had two notions of flatness. She had a relative scheme of flat presentation by ring topos. There was one notion of flatness, namely that's a morphism of ring topo identified should be flat. and another that it should come from a morphism that should come locally from a flat morphism of usual schemes, you see, of finite presentation, morphism of finite presentation that is flat of usual schemes by a pullback, which is stronger, you see, which you couldn't prove. That's the other saying. But it's a little different to see this context of relative schemes. Relative scheme, I'm not sure it's really, you can do it in any case as a structure. I wouldn't very much doubt it, no. Doesn't look like an otherwise structure in the topos, relative scheme. You see, just like a scheme over a ring wouldn't be an algebraic structure within sets, you see. I'm not sure, you see, after all, I mean, there's an underlying topological space and such things, you see, it's in this gluing together of, yeah, it's hard to express it as being a structure on a set, which is such that you can express just in terms of limits and arrows between limits and some action onto the arrows.
Yeah, well, you've just reminded me, what was confusing me, or, thinking of that. Okay, so whenever I think of the standard process of adding of the axioms, starting with base objects, adding axioms.
Yes.
Yeah. Then, my mental images, are still completely thinking in terms of finite inverse limits and what you
Yes.
could do with that, rather than,
Yes.
that was totally irrelevant in this case.
Yes. Yes. Yeah,
No, that changed the two problems. Changed the two problems.
Yeah. I really have the feeling, you see, that's well expressed. Essentially, what one could call in a rather wide sense, algebraic structures.
Yeah, it means, the algebraic in this sense has really a sort of a feeling of constructible.
Yeah.
Yeah, it's really expressed as more constructible. The notion of what's a constructible is notion of structure, constructible species of structure.
It's really what I would like, what I would think like as looking like algebra after all.
It expresses that sort of an intuition in terms of.
Yeah, I guess I mean torsos I like to do as being algebra still, and chromo do them for algebras too. But topological spaces somehow.
Yeah, that's what I know. I mean,
yeah, that's I mean the limiting case. You see.
that's something that sits right in between. That's no.
Yeah. That's one field, by the way. I mean that's between algebra is almost a topological space. You see, it's kind of
Well, it's like a compact space.
yeah, completely disconnected. Yes. But there, yeah, I mean, it's a limiting case when you allow yourself non-small families of data.
That's right. That's the essential difference. Do you think you can handle? Is there a way one can handle this that systematically, and if one allowed such non-small families?
Well,
It's really.
probably, if one wants to, I mean, to paraphrase this kind of context by saying that series are presented by this and that, and this is, I mean, the whole point of this approach. One has to be, of course, very careful, because if one has a pseudo functor on a two-category delta, you see, after all, in order that the whole discourse makes sense, one has to fix the delta. It should be a real mathematical object, so it should be a two-category whose objects are limited in some way. And now you want to two-represent a functor, but it turns out that the thing that will two-represent it is no longer delta. And then, of course, one has to be very careful whether it really makes a sense to speak of such a thing. So one has to be very careful in the formulations. So one wants, after all, that's a thing that true represents, includes our theory, should be defined up to equivalence by some conditions, you see. And of course, one has some constructions in mind, and one has really the strong feeling that they're canonical. They may carry you out of delta. I can give you an example, by the way. It's kind of cute, you see. I kind of promised you to give you an example when we allow both a non-small set of finite inverse limits and this non-small set of Dike limits. You see. And let's give how things look. If you take, for instance, in a way it's kind of tempting to say, hey, topoi, as we have been working with them, they have still one defect. They're not just as good as sets, you see. There are some nice exact properties of sets that are not shared by all topoi, namely some properties involving infinite inverse limits. For instance, an infinite product of epimorphisms is an epimorphism. And on the other hand, in sets also, not only are finite products distributive with respect to arbitrary sums, but even infinite products are distributive with respect to arbitrary sums, which can be expressed by saying that the function which goes from, that's a projection from out as a property of a topos, of a general topos. This would mean that the projection from this topos to one point is essential, namely that the inverse image factor which associates to every set the corresponding constant sheaf, you see, should be commute with arbitrary products. So now the first property, you see, kind of the property that a family of epimorphisms should have a product that is an epimorphism. That's something that looks very much like a property of total disconnectedness of a space. And the latter property, on the contrary, that a function which goes from x, that's a projection of a topos onto one point, should be essential. That looks like a property of local connectedness. And when we put the two groups together, we think of topoi which share both the properties of totally disconnected spaces and of locally connected spaces. And I didn't really prove it, but I more or less convinced myself that these topoi are exactly the topoi that can be written as C-heads. We know, of course, that the topos C-head shares all exact properties of sets. You see, because limits are taken element-wise, and so everything is reduced to sets. Now anyhow, whether this is true or not,
Go ahead.
we might look at, call them, okay, strict topoi or something like this, you see, hypertopoi or so. There are, for which these exact properties are true, and take the two cases of hypertopoi, where we take the morphisms between topoi that are essential morphisms, that commute not only with arbitrary Dike limits and finite Dike limits, but also with arbitrary inverse limits. You see? And then one thinks that now one can express all algebraic structures, even involving arbitrary inverse limits, and in such a way that a morphism between these topoi now should transform the structure of this type into a structure of this type. All right, and so one thinks, all right, now let's do universal algebra, working with these here, and let's look at the classifying hypertopos of some algebraic structure. And now, what can come out? You will see that it's kind of. So let's take, for instance, an algebraic structure defined by a category C with a small category C with finite inverse limits. As usual, by taking for every category E in which finite inverse limits exist, we take the category from sex CE that will be T of E. So just saying that one might think of taking hypertopoi with those which have all these exact properties and taking functors between them that are essential, morphisms of topoi that are essential, in order to do universal algebra even better in a way, in some respects, because even stronger structures, I mean, even more general structures can be dealt with, in which
in which even infinite products, for instance, arbitrary infinite products, are considered.
So you can
for
kind
data. Now I was going to see how one could possibly construct, you see, the universal hypertopos, the classifying hypertopos for an algebraic structure like groups or such a thing. Let's say an algebraic structure that is defined in terms of a small category with finite inverse limits by taking, as usual, this stuff. And so let's see. So let E be now a hypertopos, and we want to express T of E as being morphisms of within, let's say, delta prime now. Let's say this corresponds to all hypertopoi. I want to express this as morphisms within delta prime of some hypertopos into E. So I do it in various steps. First, left exact functors here. They correspond to morphism of topoi of C hat into E, but not yet hypertopoi. And this is the usual thing. Because these are delta functors. And that's it. On the other hand, how does it go? On the other hand, to say that E is a hypertopos, let's admit, although I didn't really prove it, just means that's it, that it is of the type C prime, call it what do I know, that is of the type D hat, let's say, where D is a small top, whereas E is a small category, which is in fact uniquely determined in terms of E, if we assume that D is Karobian. D would be the category of all essential points of E. I mean, the essential topoi and Karobian categories determine each other mutually. Now you see, call this category here, call this R. Now, to give a functor from R into a category D hat, of course, D hat is the same thing as to give a functor from R times D naught into sets, isn't it? Because D hat, that's just complement functors from D to sets. And what do we ask of this functor? We ask of this functor here for the time being that it should commute with arbitrary like limits and finite inverse limits. This corresponds to left exact functors here, which we're interested in. And on this here, this would mean that we're interested in bifunctors here, which for, yes, that's it, which for every fixed element in here, as a functor from R into sets, should commute with arbitrary like limits and finite inverse limits. So we can use the category of these as being the category from D naught, comma, category of fiber functors on R. So let's say category up to take the inverse category, the opposite category is from underline D naught points of R. So T of E can be viewed as being from lower delta of R into E, and also as being, if E, if you remind that we call that E as D hat, as being from underlined of D naught, I'm sorry, now of D into point of R. Those points of R was the opposite category of the category of fiber functors, but then I guess you have to put an upper node here. That is that we have to see, E corresponds to D, you see, and we have to see a universal way of mapping a small category D into the category of points of C hat. Which category of points of C hat, by the way, is the category, yeah, I'm sorry, it's not C, it's N. Yes.
post here. It's post C, yes. This category of points is just post C. I mean, we kind of know this because the points of the topos are the set symmetric up to taking the opposite category as the kind of set symmetric realizations of the structure. And this is end of the representable ones. I mean, this is a little story I told you. So we know that the points of the topos C hat is just post C, and that means that the fiber functors of topos C hat is end C. Or end C naught, or end C. Post C naught, therefore, all time. But on the other hand, you see, to map D into a category is the same thing as to map the head of this category into D head by an essential functor. And therefore what we find here is, in fact, the unique, if there is any solution to our problem, it can only be, you see, it can be only the essential topos points of C head, namely yes, post C hat. You have to see all possible ways of mapping D into post C, and this would correspond to all possible ways of getting essential functors from this into this. The only trouble is that post C has a tendency not to be a small category. And so from post C hat in a way, just we get out of our universe. But there we have something very canonical, you see. Which in a certain sense certainly does after post C, I guess it probably does the drop even if post C is large, but this would be no longer a topos, you see. It would then not have a small set of generators. It would be a pseudo hypertopos. And I guess it would be true. I'm not sure. I really checked it. Even in the case when this is not small, probably it is true that this object, you see, 2 represents the theory which we wanted to represent, except that it doesn't make that much sense because this object doesn't belong to our data prime anymore. So, taking for instance, take for instance groups and take for instance, that's it, take for instance groups in hypertopoi, and you want to construct a universal hypertopos set carrying a group. So admitting that hypertopoi are constructed are just the D heads, which is plausible, although I didn't quite prove it. Then you will see that the construction gives us the following. We look at the category of all groups. That's it. We take the opposite category of this, and we take the head of this. That means we take the category of all functors, covariant functors now, from the category of groups to the category of sets. That is not unfortunately the hypertopos, but it's almost one. It's a pseudo hypertopos. And this does the job. Of course, one feels a little at ease. One would have to look up very carefully what these constructions mean when one really gets out of delta. What meaning can we retain? With respect to universes, there is an idea of somewhere else which has never, I think, been
really looked at carefully. There's a little trouble with the universes because it's, in order to be able to work with them, one has to add such a strong axiom to set theory about the existence of universes. Once one acts as an axiom, one is in a way happy to see because one has a lot of leeway in order to do category theory. But of course, axiom, for instance, assume that using all for instance, Dell'Ini just has proved it seems a beautiful thermodynamic base conjectures, and I guess he has used a large part of all the formalism on detailed homology. I'm pretty much convinced that he couldn't do without it. And now all this, you have all these topoi, you have all this nonsense, and you have used universes. But it's an exceedingly strong axiom on the set of sets. Even granting that the traditional theory of sets is non-contradictory, you see, it's possibly contradictory when we add this.
You have an axiom.
When add an axiom like this. So that's the
what is
proof of base conjectures.
I don't think, let's see, I mean, what is
Depend
the
on
axiom?
of universes.
No, I think there's a relative consistency, but I think.
Is there? I don't think so.
I thought
I
that
did
was
see,
there.
10 years ago or so, when I first came up with this intensive use of universes, I asked the philologicians, and they seemed to be convinced that it's a very strong axiom and that there is no hope of proving relative
Maybe not.
consistency.
What's the,
It would amount, I mean, the non-contradiction, I think, would more or less amount to the non-contradiction of asking that every cardinal is majorated by a strictly inaccessible cardinal. That means a cardinal which has a property. That's a little bit cardinal, that whenever if you have a cardinal that is strictly smaller, then 2 to C should be also strictly smaller. And then now comes a very strong property. Whenever we have a family of cardinals all strictly smaller, such as the indexing set is also has a cardinal strictly smaller, then the suits would also be strictly smaller. And of course, one can prove the existence of a single strictly inaccessible cardinal except for Aleph Nortus. And so therefore the question do base conjectures depend on this axiom? I mean, everybody of course would be convinced that it doesn't. But some man he thought about introducing galaxies that are universes that are kind of small, you see, that are known to exist, in which you may make all axioms of universes except that's the axiom about the union, you see, that if sets belong to the universe and if the indexing sets indexed by some indexing set I, and if I belongs to the universe, then the EI should belong, that the union suit of the EI should belong to it also, which corresponds more or less to saying that the suit of these cardinals, you see, should be still strictly smaller than the certain cardinal we picked. And his observation was that in most cases when we need this axiom of set theory, that we can take unions of sets. It's one of the basic axioms of set theory, and we want to build it to be true in the given universe as a model, so to say. That in most cases we kind of know that the EIs are already contained in an ambient set which is in the universe. So in a way, and so he proposes to call galaxy and something which satisfies the axiom of universes, except that this very strong one is weak. And now these things can be at least either can be easily shown to exist, or it can be easily shown it can be easily shown that their existence is not contradictory of set theory. It's not, you see. This corresponds to taking cardinals that are inaccessible in a weaker sense. Namely, I think it just means it's inaccessible in the weak sense. What would it mean then? I think if you have cardinals that are what will it mean? It's a limiting cardinal. You know what else? there's a little more to it. Don't remember.
What's the strong index, isn't it?
No, but no, now cardinals that one can really construct, you see.
Oh, constructed.
No, maybe it means it corresponds, I think, to inaccessible ordinals. What would it be? Something about the index, I think. Maybe pi, if pi over alpha, that's the cardinal of alpha is equal to pi over alpha of the indexing ordinal. I don't remember. Anyhow, so galaxies, in fact, which require a lot less, and then see if one can work with category theory using galaxies instead of universes. So of course one has to be very careful in a certain number of existence terms. You see too, when one work, for instance, I mean, when one constructs injectors and such things in order to do numerical algebra, to see if you can construct them in this more general context. In a way, it's more general, you see, because you have generalized the notion of the universe. So it's not normal. But you have to be more careful. That means that the axioms you have in your theorems, probably they can all be reformulated in this context, but being very careful in the assumptions. Sometimes you see you have to assume that some cardinals are majorated by a cardinal belonging to the galaxy. But I wonder if it would be enough, you see, to do most of the things one does in homological algebra and État homology, for instance, and such things. You see, practically, when one works with categories and one wants to have elbow freedom, you see, one goes, only 2-3 steps higher. I mean, that's about the most to see. One has the feeling that if one allows sets of probability 2 to the 2 to the 2 to the c, for instance, where c is a kind of continuum, one has already a lot of leeway. And when one gives ourselves even, still more leeway, let's say, with Aleph 0 numbers of such exponentiation, one should be able to do everything. What one has to write down, maybe it's possible, you see. Galaxies perhaps are the right thing, I don't know.
Well, there must be some conjecture about groups that the smallest group that they fail for is something that's cardinality higher than 2 to the C.
Uh-huh.
You know,
But it exists.
yes, probably, yes. So, I mean, you can't get all a group there just by limiting yourself to a small set. Relativism.
No, maybe, the size one has to take, these galaxies may depend on the context one is working in. But at least it would be nice to have a context where on one hand one doesn't have to throw in new axioms to set theory. And second, that one can really, without too much afterthought and trembling, one can work with categories and take the home underlines of C to C prime as being another category, etc.
Right.
And including large categories, you see, taking the kind of groups or sets belonging then, of course, to a certain galaxy. And one requires some care to see if it can be done.
It's annoying all this logic. Especially when
One wants it nice and tidily sitting on the side, you have to pay attention to it.
but you're not even sure that after you do it that you're still consistent.
No, but axiomatics, you can't ever hope for anything more than that in axiomatics, especially if you're axiomatizing set theory.
It's too bad.
I guess, well, I don't think it's so, I don't think it's so annoying enough.
Well,
I think there's mathematics behind all this. That
there's-
seems pretty clear to
There are
me.
theorems in a billion groups that say that a particular well-defined group is direct sum of cyclic groups if continuum hypothesis holds. So you'd like to
What is this thing?
a particular well-defined group. Okay.
Can you tell, kind of?
It's, I believe it's X of two other billion groups.
Oh, yeah.
Okay, I'm trying to think now which two are on it. I think one of them is the, I think it's X. One of them is the Proofer group, which I don't know if you're familiar with.
It's a well-defined group.
Yes, two well-defined groups. One of them is just the completion of direct sum of cyclic groups. And the other one is another group. Two well-defined P primary billion groups. You look at X
Favorite
to them.
groups.
Well-defined groups.
Yeah.
And the theorem goes that if the continuum hypothesis holds, then this group is a direct sum of cyclic groups. No, not at all. But if. Maybe you.
But I heard about such theorems, I think by Rose, who is a Norwegian mathematician, or Swedish.
Swedish.
Swedish, He proved such theorems with if and only if. He
Is that so?
had some very simple looking ring or category or whatever it is, and he would prove that, very explicit.
If and only?
Yeah, that the covariance dimension of this is, let's say, finite or equal to 3. If and only.
Is that so? Because you would certainly like to think that an abelian group is either a direct sum of cyclic group or it isn't.
Well, that's like saying as this proves, that's like saying you're hoping that the continuum hypothesis is true or false.
Well, I
It's
guess
not,
it's
independent.
It's kind of nice. It means therefore that some things are, which look very down to earth, are in fact undecidable. Well, large part of the mathematics we are doing, usually, it's kind of big framework. But it's not like.
It always annoyed me the fact that if you change the model for your set theory, then you throw in different cardinals. Okay. So you deny the continuum hypothesis, you can substitute it by various other hypotheses and throw in different numbers of cardinals. Okay. Well, every time you throw in some different cardinals, then you have groups of those cardinalities. You're changing all the groups. And you change the set theory. That's like it's really. It seems like in some sense they don't really exist.
No, they don't.
And I feel that since in my field the groups are all characterized that are countable, they're only when they get bigger than that they start getting interesting. I begin to think that maybe the whole field doesn't exist.
Oh, actually, it's pretty clear that it doesn't. It's just.
It's sort of annoying to work so hard on a problem and then realize.
No, it's just exists in the same sense as a particular chess play. It's just a construct of ours.
Yes.
Well, you look around in nature and you want to discover any of these things.
I honestly believe that as a point of philosophy that there's nothing infinite in the real world. Everything's fine.
Yeah, only we have to be crazy enough to
That's right.
think up and such.
Started with canon. Well, I guess it's not so.
That's kind of nice and base conjectures are proved.
Is that true? They are proved, assuming
I just
the
got a-
existence of universes.
Well, I mean, that was a joke. I just got a letter from Illusi telling me that he had proved that he was explaining in all details the proof in Cambridge at the symposium.
That's it?
And I'd like to it in honor of Hodge. Yeah. So that's one of the most beautiful things ever proved.
Now I don't know what's the joke. I don't know.
No, I mean, the joke is that I mean, it's quite clear that he will have used entire chronology. Entire chronology after all, I mean, that is all the seminars, all those topoi.
And they're all put in the framework of universe.
Universes. Oh, I see.
Yes, I mean, most
And that's the axiomatic frame.
Most variants to semester for begin that Julian universe. Because is that one has a feeling that, that all this, that there's something, there's some hardcore you see, etymology, and that is, and you have computed it and done a lot of
very precise things on it. That's the hardcore. And that all these categories, universal, etc., it's some kind of, you see, floppy thing around in order to make the parser, you see, more appetizing. So it's something like a psychological pointing or oil also.
In order to sell the product.
Yes, in order to make it understandable to oneself, you see, somewhere I mean, we have to put in some categories. They may be pretty small, etc. But to explain the things, you see, if you can take all your home underlines and whatnot. If it's the whole axiomatic setup, of course, you can do, I guess, mathematics without axiomatizing almost at all. You see, you just repeat every time instead of applying a certain theory. You just do your proofs all over again, but just do them. You just wouldn't end up with the kind of things we're doing now. So one doesn't really feel that universals are so essential. In any hard, certainly improved. After all, they were certainly improved. Independent, I mean, before base conjectures using some of this stuff about the typology. Of course, one could say that only makes sense without universals, because the typology has to be constructed in terms of universals.
Just to be amusing, are people going to turn back around now that he's proved that they're presumably true? Are people going to say, now can we get a proof without atypical homology? In other words, could one have gotten a proof that Way could have understood?
I doubt that Way could understand any proof of this. And probably wouldn't want to. But I really don't know, you see, because abstraction. Even the geometric formulation, you see, I mean, of base conjectures in terms of the so-called standard conjectures, and they can be formulated without reference to any specific multi-theory. The real core of it, I mean, is the positivity of certain traces that can be expressed as certain intersection multiplicities. I'm not sure one can completely write it down, you see, as being a mere statement about algebraic cycles, except making it really still stronger than it is by using algebraic cycles up to numerical equivalence and saying.
That's funny. That's funny because that's what you told me not too long ago when I was asking your feeling on them. But, they're just statements about cycles.
Yeah, but then one should make them still stronger. You see, that would mean that at the same time, morally one would prove then that numerical equivalence for cycles is the same as logical equivalence. Maybe linear proves it at the same time also. But then the whole yes. Yeah, I guess so, yeah. One should be able to formulate the whole thing. That is to construct motives completely independently, a restricted theory of motives without any reference to any specific logic theory. I mean, then the motives are the logic theory. You see. But Lucy tells me that, I mean, the most essential use is made of SGA7. I mean, SGA7 was all about Descartes homology. But there was some also, I mean, some relations with Korean homology, etc. Anyway, it was all in the framework of homology.
kind of curious to know what the ideas are, because
You spent some time thinking
don't know.
about them.
yes, I have the impression that it was close to him at all.
Well, maybe you could fly there on your way back. Get the Aeroflot pilot.
Shall we go with some red beans tonight?
And I think that we'd probably continue this discussion just as well.
Yeah,
with
absolutely.
full belly.
Yeah, or speak of something else.
Goes to y is said to be epimorphic. If for every x, this map from hom yx into the product of hom yi axis is injective. Namely, if a map from y into x is known, if we know its composite term, is y equals to y. Then it's said to be epimorphic. But that's still kind of a big notion in many cases. Too big. What we want is, in a way, to reconstruct y as a function of the center of the yi's by something like an equilibrium, the description of yi's, and then modify the other products. Here, for simplicity, I assume that there are the other products according to this survey. And that's what is just expressed, I mean, in this technical way. In this case, you say that the strictly epimorphic. And so, the property here that C goes to C hat factors through C tilde, namely that the principal functors on C constant functors are shields, just means that the covering families are strictly epimorphic families. In fact, in all topologies on C, there's one which is the finest, which has properties. The finest means which has the most covering family. And those for which we take as covering families of Y not all strictly epimorphic families, because this may not be stable under base changes, so it may not be a topology. But those which are strictly epimorphic which remain so under any base change. And that turns out to make a topology that comes out of it. Not formalism, as it's explained in here, it comes out very nicely. So, to say that C goes to C hat factors for C tilde just means that the topology we are dealing with is less fine, is coarser than the canonical topology. It's a topology where the covering families are the effective, as the universal strictly morphic family of modes. Alright. Now, when this is so, then we may identify every object of C to the sheaf it defines. In fact, this functor is, in this case, fully faithful. So, instead of identifying object of C to object of C hat, you see, which was very handy in all questions, where only inner limits came in, but which was kind of unpleasant as soon as like limits would appear, because this here had no tendency whatever commute with any type of like limit whatever. But we will use C as being within the capital C hat. And you see in the capital C hat, the relations between inverse limits and like limits are just perfect. I mean, it's just as good as in the case of sets. And you can very safely work in this category C hat. But we will be careful to, when we look at like limits in C, to restrict to those, in many questions at least, which are also like limits in C tilde, so that we are perfectly safe as to the relations between like limits and inverse limits. For instance, that passing motion commutes with taking products and such things. And therefore here, the topoi appear in the natural way as being kind of big enveloping category of category C, which has enough exactness properties, so that one is really safe for whatever one wants to do in geometric terms. You see, one wants to have a formalism which works as well as a kind of sets. So C itself may be kind of kinky, it may have bad properties, because for instance, percentage quotient may not commute with space change, that's the kind of schemes or something is wrong with it. So then let's say that percentage quotient
which is not also a transition function, C tilde is kind of pathological. It has to be dealt with great restraint, you see. But we will mostly insist on trying to discover criteria for types of diagonals here, like transition quotient, to be in fact already transition quotient here, which is strong probability. And then whenever we have such situations, then we are perfectly safe. But in some cases, I mean, this has turned up only after a few years one has used this. One has also to deal with situations when C as a subcategory of C hat does not lie in C tilde, in which therefore representable functors are not necessarily sheaves, or it amounts to the same where the topology we have on C may not be coarser than the canonical topology. So in this case still, it's good to have a functor from C into C hat, from C into C tilde, by taking the compositor of the inclusion here together with the associated sheaf functor. So in all cases, we will define a canonical functor from C into C tilde by writing epsilon C of x is equal to A applied to x when x is identified with the object of C hat. Now beware that this functor will be fully faithful now if and only if C is already contained in C tilde. Epsilon is C, therefore goes from C to C tilde. Epsilon C is fully faithful if and only if that's an easy exercise. C is contained already in C tilde, in which case epsilon C is just an inclusion functor. That means if and only if the topology of C is coarser than the canonical topology, which is fortunately true in most cases. But if it's not true, once again, we have to use this functor, being very careful about the fact that it's not fully faithful. Therefore, we should rather not identify C as a percentile of C tilde, because the Holmes one would be the same. So then, of course, this yoga of viewing C tilde as being a kind of a natural embedding for C no longer works. It's kind of an envelope, but it's no longer faithful. You lose something from going from here to there. But still, what is true is that the image of C and C tilde is a generating subcategory. Well, I think that's pretty clear, I guess. So in order to see that it's a generating subcategory, that's the set of all epsilon C of x's where x goes over C generates. So we have to look at the homomorphisms of this and to an arbitrary variable sheaf f of C tilde and to see that the set of functors from epsilon C x f, that this family of functors for variable x is conservative. These are being viewed as functors with respect to f. Now, as epsilon C of x is a sheaf associated to x, this is just home. This here is the home in C tilde. This is just the same thing as the home in C hat of x and f. And this itself is just f of x. So the functors we are interested in are just the functors which associate to every sheaf, f, its value on a fixed element x, and it's quite clear that the set of these functors is conservative. Therefore, provided the category we're working with C is small, we get it this way, a set of small generators, and therefore C tilde is a topos.
In fact, it's very convenient to work also with sites which are not small. For instance, among all possible ways to define it, to get the topos as being equivalent to a C tilde for suitable site C, there's a canonical one by taking C equals to E. We can always view a topos as being a site by just taking the underlying category, taking the canonical topology on it, and in fact, because a topos, they call the strong exactness properties of the topos. In topos, any epimorphic family is universally epimorphic and is strictly epimorphic. Because every epimorphism is a strict epimorphism. And of course, to say that then family xi goes to x is strictly epimorphic means that while finite products exist and like sums exist, and that products are distributed with respect to sums, just means that the sum of the xi goes to x is epimorphic. So the canonical topology in a topos is just a topology in which the covering families of an object X are the epimorphic families. And it will turn out that any constraint functor on E which transforms, which is a sheaf for this canonical topology, which has a property that whenever we have an epimorphic, so it transforms sums into product, and whenever, let's say, we have an epimorphism x prime goes to x, so that we have this diagram here with x second the finite product, that then fx goes to fx prime goes to fx second in two ways. Every functor for which this is exact and which transforms sums into products will turn out to be representative. Therefore, the map, let's say, which we have seen in general, which goes from C to C tilde, for any site, when we apply it to the case of the site defined by a topos with a canonical topology, will be the map from E to E tilde, which will be just an equivalence of categories. Every element here is representable. So that among all possible ways of writing a topos as being of the type C tilde, the best one by taking the whole topos itself as a site. Just as between all possible ways of generating a group, method of generators, there is one quite canonical by taking all elements of the group, you see. And this reason, because one won't like to write down such things, you see, to view a topos as being a particular type of a site, so that we don't have to do everything twice, you see, for the sites and then for the top point. We're sure that whatever we do for sites can be applied directly to the top point without first choosing a generating site for the topos. You see, it's handy to be able to deal with sites which are not small categories. So that's an important technical reason. So we started with small categories for sites, and then very soon we became quite annoyed because many categories which turned up, which one would like to look at the sites, are not small. Anyhow, the definition of a site doesn't make use of smallness, nor the definition of C tilde. However, if you want to already to construct the associated sheaf, there's a direct limit to take over a set which might be just too large to be a set. I mean, we may get functors from C as an associated sheaf. It may turn a limit of C into a set which no longer belongs to the universe we like to work in. So that's the real trouble, you see. So we have to make some axioms on C which ensure, for instance, that taking an associated sheaf doesn't carry us out of the universe. And the axiom here is the axiom of a so-called U site, where U is the universe we're working in. So it's a site which, first of all, is a U category. This just means that the home sets within this, for the two objects in the site x and y, home xy, should have a cardinal which is small, should be larger than, which should be as large as the cardinal of the whole universe we're working in.
And second, there should exist a small generating family. A small generating subcategory C0 of the site. Now I have to use the notion of generating, not for the abstract category structure, but for the site structure. I have to define what I mean by this. And it's pretty natural. I say that a subcategory C0 of C generates the site, whether C0 is small or not, makes sense. If for every X in C, there exists a covering family of X, where all the Xi's are in the subcategory. I want that to be able to cover any object of the site by some of these objects. Then it turns out, in fact, that if we restrict attention to this subcategory C0 and with the so-called induced topology, that's a technical definition which I don't want to make precise here, but I mean it's pretty clear, relatively evident notion. Then the inclusion of C tilde and C will define by restriction. If every sheaf on C restricted to C0 will be a sheaf, that essentially the definition of the induced topology. That's the finest of course is topology. C0 which has this property. Alright. And this would be an equivalent of categories. You see, I mean this explains a posteriori because this is the theorem in a way. Why, when we have a site which is a U site, I mean, in which there exists such a small generating subcategory, then things are just as good as if the site was small and the need not caution. In any case, the existence, for instance, of the before proving the theorem, which comes later, this is a so-called comparison lemma. Yeah. So let's, one can show that if C is a site which need not be small, which is just a U site, which has this property of being generated by a small site, then the functor from C hat to C tilde exists. I mean, the sheaf offset to the pre-sheaf doesn't carry us out of the universe. We still have sheaves with values in the category offsets of the given universe. We don't have inverse like this, which are just big.
What's an example of that?
That we get out of the universe.
No, but an example of a U site. So it's not already.
Any one of the things that you have seen so far, you see, practically, except, we have not seen any non-U site for the time being. A better question would be, what's an example of a non-U site?
Okay. Well, yeah.
Yeah. Take, for instance, take all schemes, or if you prefer, if you don't know what schemes are, all Arenal white spaces over Z, let's say, over a field, over some ring. And take on this, so it's a very big thing, with your own schemes. It's a big category. And take on this the any topology you want, take the restricted topology which you want, or basically flat topology or something like this. You see, really there is no generator. Because really, there are schemes so big that you can cover them by a set of a given family of schemes. Just take a family of fields of increasing transcendency degree beyond, which gets to cardinals beyond any limit, you see. So, but however, you see, with these sites, one likes to work, but one should be you see, when one really wants to give actual proofs, you see, one should be careful when it's constructing associated sheaf to a pre-sheaf. To be very specific, then one has to be very careful that the sheaf, you see, is really with values in the same universe, that the indexing sets that occur are not too big. And in fact, it's not clear because the indexing set that will occur in the examples I gave is really just too big. But for some pre-sheaves, you see, one is lucky, you see, one can show that.
Okay. That's good.
All right, so what one should recall, I think, is that there is no caution to have for sites which are not small, provided they are loose sites. That everything is just as good as if the site was small. Now, let's go on now with the series of theorems. There are two theorems which go together, which essentially say that to give a topology on the category C, a localization is the same thing as to give a scatter of sheep. This is to 0. I mean, that's really a very nice situation. So if C is a category, you always do as being embedded in C hat. So if you have a topology T on C, to this is associated the full subcategory E lower T, let's say, of C hat. CT, let's in fact a strictly full subcategory.
You mean strictly?
It contains, with every object, it contains all those that are isomorphic to it. Say tilde because of shield. And so the first theorem will tell us how to recover a topology from knowing the killer of shield. And the second theorem will tell us what are the subcategories of C hat. And in both cases, I mean, the answer is just as simple as one might dream. So let's say first, so maybe we state it just as one theorem. They were separated by a pretty heavy and rather irrelevant section in our seminar, and I don't know why. It's a pity because really they should go together. So first of all, how to recover the topology? Well, a family Xi is covering for T if and only if the corresponding family of morphisms within C tilde is epimorphic. That is, I just view C tilde as being a kind of an enveloping category of C, and whatever I do in C, I look at its image in C tilde. Now, this would be a description of the topology in terms of the category C tilde if I make sure that the functor epsilon C, which goes from C to C tilde, is defined directly in terms of the subcategory. But that's clear because the first nicest case was of course the one when C viewed as being the subcategory of C hat was contained in C tilde, in the case of topologies which are less fine than the canonical topology. But in the general case, we have defined this functor epsilon C to be the compositum of the inclusion and a functor from C hat into Et, which is the left adjoint of the inclusion, which therefore after isomorphism is also defined independently of the topology is defined directly in terms of this subcategory. All right, so this is a perfectly good characterization of the topology, the covering families of the Grothendieck means, in terms of the category of shields. So in terms of covering C's, you see, if you have a subobject R and X, then now R is an object of C hat, of course, X being an object of C, then this C is covering if and only if AR mapped to AX. This would be, of course, a monomorphism a priori because A is less exact, but if this is not only a monomorphism but an isomorphism. So if you use language of C's, you see, covering C's in order to define topologies so that you no longer have to use private products in C. You have also this characterization. And so this would, the theorem itself would be the theorem 2, and the theorem 1 was the existence of the joint functor, the left exactness of it. and the fact that it was L composed with L. So that's the first thing. Now, the second question is, what are the subcategories of C hat which we obtain? And we know already an important property of them, namely, they are strict full subcategories, such that the inclusion functor admits a left adjoint and two cells. That's all. For every E in C, strictly full subcategory of C hat, strictly full subcategory, such that exists in a joint functor A of C hat into E left adjoint to E goes to C hat with inclusion. There exists T on C such that Et equals C tilde. That's such that E equals C tilde equals Et. So there's a one-to-one correspondence between topologies on the side C, notions of localization on the side C, and all subcategories of the category of species which have this property. Now, what does this mean? Let's say that in more geometric terms, as we have already the language of topoi after all. C hat is a topos, C t is another topos. Oh, I'm sorry, a left adjoint, which is left exact. Hey. Which is exists A, left exact. Yes. Has to be left exact. Okay. Well, so we have A lower t on the one hand and I lower t on the other hand, where A lower t is left exact of I lower t, and A lower t is a functor that commutes with left exact. Now such a pair can be viewed as being a morphism of topoi of C tilde and C hat. And in fact, this here is a morphism of topoi in which the direct image functor associated to it, which is the inclusion here, is fully faithful. Now, morphisms of topoi for which the direct image functor is fully faithful, they, in the case of topological spaces, take them sober to play safe, or not even so. Assume that you have a continuous map of topological spaces. So it defines the morphism of top x and top y associated with inverse direct image functor f star. When is it true that f lower star is fully faithful? One can see that it's true if and only if the topology of x is the inverse image of the topology of y by f. In the case when the spaces are sober, this just means that f is a homeomorphism of x onto its image. And therefore, if we follow this analogy, and it's a perfectly valid analogy, by saying that the morphism of topoi is in a topological embedding of topoi, which makes the first topos a subtopos of the second, whenever by definition, whenever the direct image functor is fully faithful, then we see that here the topologies on the category C just are in one-to-one correspondence with the subtopoi of the very special topos C hat. But subtopoi, you see in the geometric sense, in the algebraic sense, correspond to quotients, because to say, if you have a pair of adjoint functors, here we have the direct image here and the inverse image there. To say that this is fully faithful means that this here is a passage to a category of fractions. If we take and C hat all those arrows which become isomorphisms by this arrow here, and if we make them formally invertible, then we will get back the category C tilde. That's John's statement about pairs of adjoint functor. One of them is fully faithful if and only if the other is a passage with fraction by a set of arrows. All right. Now let's go so we have an interpretation of the set of all subtopoi of the topos of the type C hat. They correspond to all possible topologies on the category C. exactly. And in fact, you see, when we are going to apply the language of topology to universal algebra, I mean, subtopology of a given topos, which quite often will be of this particular type C hat. When this topos is viewed as being the classifying topos of a certain type of algebraic structure, is just the subtopology just corresponds to more restricted types of algebraic structures which we can obtain by adding more axioms. And so we see that all sub-categories of structures, subtypes of structures, obtained from a given type of structure by putting in more axioms, all possible ways of doing such a thing correspond just to all possible topologies one can put on the category C. But now let's go one step further and assume already that C has been endowed with a topology T, which I don't want to move anymore, and C tilde, let's say this is the topos E, which I assume to be given already. Maybe it's already the classifying topos of some kind of algebraic structure, which I could construct in terms of a certain site. And most cases there's some other natural sites to define these topoi. And I'm interested in finding all subtopoi of E and all subcategories F of E which are strictly full, and such that the inclusion factor has a left adjoint which is left exact. Now I claim that these are in one-to-one correspondence with all topologies T prime on C, which are which have less sheaves, therefore which have more coverings, which are finer than the topology T. Which are finer, that means which have more coverings. Let's see why this. Well, I mean, it's pretty clear that as C hat, as E is itself a subtopos of C hat, the subtopoi F of E and one-to-one correspondence with the subtopoi of C hat, which happen to be contained in E. Now, the subtopoi of C hat we have seen correspond to arbitrary topologies on C, E corresponding to T. And now to say that a subtopos corresponding to T prime, let's say F, is contained in E, of course means, because of the one-to-one correspondence, that T prime is finer than T. The finer the topology, the more coverings you have, the more stringent the condition for a sheaf to be a sheaf. Therefore, we see that if we have a topos which is described in terms of a site, as being the sheaves on a site, then the set of all subtopoi of this given topos is just a one-to-one correspondence with the set of all topologies on C that are finer than T. So that's what Giraud's result says. So he proved this at a time when one was mainly concerned with exploiting one particular topology, like the entire topology or flat topology, and not caring too much about the relation with others. But as soon as one systematically varies topologies and investigates subtopoi, etc., this is really a basic statement. Now there are still two terms left. May I still state them, or maybe it's a little late? Can I go on?
Please do.
Okay, Ozaki, what do you think? You don't mind?
No.
You don't dare to protest?
Is this going to be the last talk? Or?
I think so, yes. I mean, we can, if anybody is interested, we can anyhow fill in, you see, some sessions where we can clarify some questions that are asked. And then one can go on any amount of time, you see, just working out examples, you see. There are many very interesting examples, like quotient topoi by taking, for instance, when you say feuilletage, you see
Foliations.
foliations, that's it. Foliations, and you see, they may look really pretty bad, and the global quotient set may be extremely bad. But there are nice quotient topoi always associated to it, you see. And I mean, one can make go on for weeks, you see, working out examples in order to get the right geometrical feeling. But maybe it's also good to do it by oneself a little bit. So there are many exercises, after all, in SGA, which can be worked out. To get the topos which are locally isomorphic, which are locally homomorphic, wherever the equivalent to the vertical space, etc. Speaking about universal covering of such things. Doing the whole game of topology, of topoi, and seeing exactly how far, how close one is to the space. Go on for quite a while. But here there are still two main general statements which I could state. There's the one which I stated very quickly. There's a comparison lemma which says that under certain conditions, if I have a site C and a full subset with C naught, which I endow with the induced topology, which is the closest topology for which this inclusion function is continuous, namely for which the inverse image of a sheaf on C is a sheaf on C naught, you see. So it gives us conditions under which the corresponding functor will be equals of categories. So this will be so, assuming that C is a U side and that C naught is small, for instance, or a U side. Well, maybe a U side would be now. All right, a U side. This will be so if and only if this map, which was from C tilde to C naught tilde, where C naught is endowed with the induced topology, is an equivalence if and only if C naught is topologically generating. If C naught generates the site, then every object of C can be covered, the object of C naught. Now this is a generalization, so that's a comparison lemma. Call it theorem 3 if you want. So this is a generalization of the well-known fact that if you want to work with a category of sheaf or topological space, this very afternoon, I recall the fact that if you have just the basis for the topology, a subcategory of the category of open subset of the space X, such that every open set can be covered by open subsets of the spaces of this, then the category of sheaves is the same as the category of sheaves constructed with the subcategory by taking three sheaves on this particular family of open sets and the exactness property expressed just for these. And in fact, the proof essentially is the same. You see, the idea is that when one has a sheaf on the smaller category, one reconstructs the sheaf on the bigger one because every object of the bigger one can be covered. You see, assume that we know f over the category, and we want to construct f of x for the big category, but x is covered by xi's, where the xi's are in C naught, x is only in C. And well, the Hilbert products may not be in C naught. For simplicity, let's assume they are, otherwise we would have to cover these again by each one of them by xijk's, xij alphas, let's say, that are in C naught. And then f of x will be the kernel of the map going from the product of f of xi's, which are known, to the product of the f of xij alphas, which are known too, because xij alphas and xi's are in C naught. You see that? And that's the whole mystery to it. But one has to, of course, to write it down in detail. It takes up a few pages, I think, in the seminar. So this shows us how that there are really very many ways of defining a topos from different sides. write this part in the topological space. Whenever one has a base of open sets, you see, that make many different sides. Either they all define the same topos. And what is really important is a topos. Now, the last theorem would be the characterization of topoi in terms of sides. We call this theorem 4, and this will be the end of the course. We could give it by equivalence conditions on a category. So let E be a category. And we assume it's a U category, namely the homomorphisms are small sets. This by equivalence while hom x y is a small set. Then the following conditions are equivalent. So the first condition, one could like to take as a definition of a topos because that's the safest one. E is equivalent to C tilde for some small side if you really want to play safe, but let's say for some U side. And if you want to play still safer, we'll say E is of equivalent to some C tilde for a small side C stable under finite inverse limits, let's say. Because we have noted that it's sometimes handy to have finite products now to work in a side. So in order for each A to make a sense, we are supposed to have defined topology in general without the existence of finite products. All right, let's stop this matter. Now this here is really pretty safe because through the formalism of the sheaf associated to a prefix, one really feels that one can work perfectly well. And sheaves here really do have a topological intuition of localizations and having to check things just locally, etc. I mean, they are very, in a way, once one gets accustomed to it, one is on very firm grounds. And then, now this is equivalent with saying that there exists an embedded, fully faithful functor of E into some category C hat with I, which has a left adjoint A, which is left exact. All right, of course, A prime implies A implies B by what we have seen so far. In fact, by Giraud's theorem, well, let's not go to. Oh yeah, but here, what is C here? C small, let's say. C small category, because I like C hat to be a topos really. Before it's a topos, it's to be U category at least. So let's say C small. Yes. And by Giraud's theorem, B implies I prime, because if E is embedded in this particular C hat, in the way I said, then we can find a topology on C. So that E is just equivalent to C tilde, provided it's equal to C tilde, provided I replace E by its strict hull in C hat. Alright, so these three already are equivalent in virtue of terms that we have said before. So therefore call these things topoi, and now we would like to state this in terms of exactness properties, and so here, this is the standard definition that we have started with exactness properties of E plus small generating family. If you want. This again, I mean, is another contribution of Giraud, namely that this here, which of course is a consequence of these, implies in turn these. So here, there's an extra proof to give you that follow from what has been said so far. And on the other hand, we want to have a survey on all possible ways of getting E in terms of the categories of the sites E as being C tilde. And there's a corollary which complements this situation. And I'm going to describe all possible ways of getting a topos in terms of the site C in all cases where C is actually contained for those sites for which C is contained in C tilde, and for which the topology on C is coarser than the canonical topology. Those for which the functor forms into C tilde, the canonical functor, is fully faithful. And in fact, I should stay here in A prime. I could restrict if I wanted to small sites stable under kind limits, and with topology coarser than the canonical one. And in fact, the first topology one has worked with, like the Italian topology. One sounding, of course, those that come from ordinary topology. They satisfy this condition, and one is more happy. One didn't even think of using others as this All right. Now I'm looking at such sites, and I would want to see what are the various ways of realizing E through such sites. So, of getting equivalences between such as C tilde and E. So, such a category C should be naturally embedded already in E. So, we are looking for the full subset of E, which should have some extra property. In fact, the relation between, once we have given E as a subset of E, the relation between E and C tilde will be the following. Every E, well, we associate, we have a function from E into E hat, which associates every object in E, the complement function it represents, and then, because E is contained in E, we have a function goes into C tilde here. The function on C associated with it will be the restriction to C of the so the situation is the following. They are epimorphic and the meaning to it. The function from E to C tilde without the use topology, which is obtained as I just said. The element of E, I look at the restriction to C of the function as represented. Y F. Phi lower C if you want, associated together with C. Then phi C is if and only if C is a related subset. That but if C is generating, we see at once because of the exactness property of topos, that does mean that it's generating small units. But the subset of the size, so just mean that any object is but you must say with topologies which are to get a way of representing a certain suicide or to give a full subcategory of E, which generates E as a subcategory of the size that not be thinking of. And of course, there are many ways of generating E in this way. If any subcategory is any bigger subset, we will do. Of course, by the very definition of a topos, there should be small generating subcategories. So we are sure that we can always find small subcategories for which things work nicely. All right, so we will find again the equivalent of A prime with the set FE for the topos. But also, we can factorize C with respect, for instance, to find an inner limit, or to find a direct limit, or to both, and we get in this way subcategories. Find direct limit one be too useful, but find inner limit would be quite useful. And therefore get type representing E, in which find inner limits exist. And of course, the most fundamental choice, as I already pointed out, is to take C equals C itself. And do C as being the general of C on E. And then this corresponds to, during for instance, C on a space X to be the category of C on the entire space on the kind of all the entire spaces for the X, discovering them in surjective affinity. So this pretty natural, because what is the difference after all between open subject and the entire space? I mean, so that's a locally that's the same. So in a way, it's more or less the same thing here. You see, every element of E can be obtained from elements of C by gluing them together in some sense. Taking the Morphic family, you see, and take the, as I explained, by taking I equals X, so X is the quotient of the field of Xi. Now, maybe these hybrid products won't be in C anymore, but we once again color them again by elements of C so that X appears. And obtained by gluing together Xi with respect to Xij alphas. So I think I'm going to stop here. This would cover the basic facts about types and topology. So I'm going to know more about it, and we get to work with one. To know that just to work with one. So either maybe we could agree on some data pattern for meeting for speaking about relations between topology and universal algebra, or speaking about universal algebra shortly, I mean, to try to understand what is going on. I don't know. Where am I saying?
Same time or what time?
We change it to Monday.
Yeah, you want to make it Wednesday?
Wednesday?
Any day other than Monday.
How about Wednesday? Is Wednesday it?
I guess so, no?
How about Wednesday?
Wednesday, starting next week.
Okay.
Right, so same time then?
And if that suits everybody.
Yeah. So this won't be really. Here it was supposed to be kind of a course, you know. So these things that I can explain, there are things which I really know rather well. But what I'm going to follow is things they're pondered over, which I don't know well at all. You see, I have a few ideas of what might be true and what could be false, number of examples in the head. I mean, the whole work is to be done. So it's very different. So it's rather a common discussion about what could be done.